sessions. And the first speaker today will be Wanda Yu, and her presentation is on the mesospheric temperature and circulation response to the 2022 Hunga volcanic eruption. And we can see your screen this time, so please go ahead.
Okay, thank you. Thanks for giving me this opportunity to share our work using Wawg model to study the mesospheric dynamics response to the Hunga volcanic eruption. Most part of this work was done when I visited NCAR last year, and I would like to thank all my collaborators for their help in this work. Especially, I want to thank Rolando for hosting my visit and for all his valuable input. This work is based on Cesm satellite instrument observations and the vacuum simulations. One sentence key findings here is the stronger stratospheric westerlies in August 2022 leads to the enhanced mesospheric meridional circulation and thus temperature changes in the mesosphere. Since our focus is on the mesosphere, the satellite instrument that we check the temperature variation is Cesm, sounding of the atmosphere using broadband emission radiometry because its temperature product has a very fine vertical resolution in the mesosphere. The vertical grid is about 2 kilometers. This figure shows the monthly mean temperature anomalies from May to August 2022. And the anomaly here is 2022 minus the 20-year climatology. With the x-axis is the latitude from 90 degrees south to 90 degrees north, and the y-axis is the pressure covering the stratosphere and the mesosphere. The regions without hatches mean the temperature in 2022 is record-breaking. The peak of the anomaly occurred in July and August in both.
No.
Yes.
Hello?
Hello?
Do you hear us?
Yeah.
We can't hear you right now. Something happened.
It wasn't me.
And you are not muted, so you should be fine.
Okay.
Do you have any way to turn up?
I mean, this one's on the companion.
Oh. And actually, we can turn the camera too. You see us, but that's not helping. We can hear online. We cannot hear you guys, Elizabeth. We cannot hear her. I know, yeah. Just there was a bit. Well, all we did was change the layout to the sidebar.
So Joanne said they can do it.
Yeah, but only there, but not here. Okay. In the room.
Maybe we should join without the companion.
The light went red and then came back.
No, that's whether we are broadcasting out.
Oh, yeah.
It was a little bit, a few beeps and then stop. Yeah.
I can hear. Can you say something?
I say something?
We can't hear her.
No. No? He's simply before the books.
Do you hear me? I can also hear online perfectly.
Okay, well, sorry for that. Well, while we're waiting, I guess we just say welcome everybody again. Nice that you're here, and actually happy Valentine's Day for those hopefully.
Same to you.
Thanks.
I'm good.
I hope everybody will have a good afternoon or night after this meeting. It's not too distracted. But first we want to enjoy the talks, hopefully soon. And the good thing, I mean, what we could do, I guess it would be possible we could present a talk here while they hear us and move Mondi's talk to the second talk.
Yeah.
Is anybody logged into the meeting on their laptop?
Oh, to
Because
just
a laptop speaker
you
could be
hear it?
turned on.
Yeah, can you actually?
The issue is the
I log in. I was just log in,
This one is on companion.
but I'm in the main room for some reason,
Yeah,
not in this room.
we don't hear them. Wendy, can you say something?
Sure. Can you hear me?
Oh, now you can hear.
Yeah.
Yeah.
You heard
We can hear.
really.
It's just
Oh,
Oh,
that's
okay.
it's just not coming through these speakers.
Okay.
We actually hear. Yeah, I can hear from the computer.
Hi. Say something, please.
Can you hear me?
Yeah.
What did you do? Yeah.
Oh, I was just using the wrong output.
What?
It's
Oh.
output to the TV versus.
Oh, wow.
Now it
Yeah.
works. Thank you. Okay, so we
Wow.
should not change anything there? Yes. Okay, just change the layout, that shouldn't matter.
Everyone.
Yeah.
Yeah, so that should be fine.
Okay, yeah, so we
Okay.
can do this, but there we go. So, okay, please, we're good. Thanks so much.
Yeah, thank you.
Well, that's nothing yet.
Okay,
Thank you.
Okay, so where should I start? Can you hear me from the beginning of this page or?
yeah, just go ahead.
Okay,
Again from this page, so we'll remember what you said.
from say, from here, sorry.
Yeah.
So did I introduce this figure yet? For example,
Introduce it again.
okay, maybe I should start from this page. So we use SABRE sounding of the atmosphere using broadband emission radiometry to check the temperature trend, the temperature variation. Because it has a very fine resolution in the mesosphere, the vertical resolution is 2 kilometers. And this figure is the monthly mean temperature anomalies from May to October 2022. And the anomaly here is 2022 minus the 20-year climatology, with the x-axis is the latitude from 90 degrees south to 90 degrees north, and the y-axis is the pressure covering stratosphere and the mesosphere. The areas without hatching means the temperature of this month is record-breaking. The peak of the anomaly occurs in July and August in both stratosphere and mesosphere. Here we focus on August of 2022, the month with the peak anomalies. And there is a tripolar pattern that there is a cold center in southern hemisphere, astrotropics, stratosphere. A warm center in southern hemisphere, astrotropics, mesosphere. And V-shaped cold anomalies extending from the lower mesosphere in the tropics and the upper mesosphere in the astrotropics in both hemispheres. And this pattern weakens in September, and the significant anomalies dissipate after September. Next, we want to use vacuum to explain the changes. The following is the model description. We use the 70 vertical layer version, about 1 degree horizontal resolution. And the model was nudged to GEOS 5 in January and become fully coupled free running after about February 2022. We have 10 members in each ensemble, and the difference between the ensemble members is that they have different nudge end date from 27th January to 5th of February. And we have one ensemble is control case and another is the volcano case. The only difference between these two cases is that we inject 0.42 teragrams of SO2 plus 150 teragrams of water vapor, following the instructions of Zhu et al. 2022 paper. Then this is the vacuum result. Here the anomalies is the difference between the ensemble mean of the volcano case and the control case. And the areas without hatching is the difference has a p-value less than 0.05 in t-test. This signal of delta t increase significantly over time, reaches a peak also in July and August. And this structure, and we see the same structure, and this structure dissipates after September. So we can conclude that the vacuum simulation can reproduce most of the features of the temperature changes in 2022 as observed by SABRE. Last slide is the ensemble mean, and how about the ensemble members? We focus on this month, August 2022, with the largest response. Here, the left is the temperature anomalies from August in SABRE, and the right are the 10 ensemble members. So we see all of the ensemble members can successfully reproduce the spatial pattern, and the 6 of 10 successfully reproduce the magnitude of the temperature anomaly as observed. These statistics of the ensemble indicate a robust causal relationship between the Tonga volcanic eruption and the observed mesospheric temperature changes. We are also interested in the changes in circulation. This figure shows the transformed Euler mean wind field in the mesosphere and the stratosphere in the control case, volcano case, and their difference. Here it shows the mesospheric meridional circulation. This circulation is from the summer hemisphere to the winter hemisphere, and it is caused by the gravity wave breaking. And this figure that shows the difference, the red color means a strengthening of the circulation, and the blue color means a weakening. And the length of the arrow in the difference figure is 20% of the original field. So there is a strengthening in the mesospheric circulation by about 20%. The changes in the circulation can explain changes in temperature. For example, in the lower mesosphere, southern hemisphere, the stronger downwelling increases the adiabatic warming, and the stronger upwelling in the upper mesosphere in both hemispheres increases the adiabatic cooling. This figure is still August 2022 Wacom 10 ensemble mean temperature anomaly with the contour to be the ensemble mean, zonal wind. Here we chose this point, temperature at 0.1 hectopascal 60 degrees South, where there's a significant temperature anomaly. And the zonal wind at 5 hectopascal 45 degrees South, where there's a strengthening in the westerlies. As the x-axis and the y-axis of this plot, this is autumn control cases. We have this scatter plot of the control case mesospheric temperature and the stratospheric westerlies. Then how about the volcano case? As shown by this red color, we can see in all 10 cases, when the stratospheric westerlies shift towards stronger anomalies, the mesospheric temperature also shifts towards the wind also shifts towards westerlies. This suggests that there is a causal relationship between the changes in stratospheric westerlies and the mesospheric temperature. And on this page, I will show the mechanisms of this causal relationship. In this figure, we show the zonal wind in the control case, volcano case, and the difference. This is still the vertical distribution covering the mesosphere and the stratosphere. The stratospheric westerlies in the southern hemisphere become stronger in mid-latitudes. And the changes in the zonal wind can cause changes in waves. In the following figure, we show the sum of the gravity wave and the planetary wave drag in the control volcano and their difference. The negative total wave drag become more negative over southern hemisphere. This is because the stronger westerlies in the stratosphere filters out more eastward gravity wave that enter the mesosphere. So the total wave drag in the mesosphere become more westward, so more negative. So we see a strengthening in the wave drag. And because the wave drag drives the meridional circulation, the strengthening in the wave drag can cause the strengthening in the meridional circulation over the southern hemisphere, and thus drives a change in the circulation globally. And the changes in the meridional circulation can drive the record-breaking changes in the mesospheric temperature. And this is the whole process happened in August 2022, caused by this sudden change in the stratospheric westerlies. I also include a page of other interesting Hanggang-Tanga related questions. We are also interested in what causes the changes in the stratospheric dynamics in August 2022, and we are currently working on this. We are also interested in will the polar mesospheric clouds be influenced by the Hanggang-Tanga injected water vapor? If so, when will this happen? And there are another two very important questions. Will the injected water vapor enter the polar vortex and cause possible ozone depletion? When will this happen? And the details of the ozone chemistry and the climate impact of the Hanggang-Tanga volcanic eruption. Will the sulfate aerosol cooling or water vapor warming be a dominant process of its climate impact is still under debating. Here I put the conclusion page here and a QR code of our paper. Please check it if you are interested in it. Thanks for your time.
Any questions?
Really nice talk. Wacom did really well in what, 6 of the realizations or something like that. What happened to the other 4?
The answer is we don't know. So as I showed, the only difference is their nudge end date, which is about at the beginning of February. So actually there's like at the beginning there is a very little difference. And for all the 6 cases, they are independent of this nudge end date. Here. So we also checked other, like, is there a precursor for these changes? And we found that there is no, and another information is that for July, there are also some strong cases and weak cases, and they are different from the cases in August. So we think this is like a random process.
Well, we run with different oceans. So the ocean is free running in these runs. And if there is differences in ocean state, I don't know if that could cause it. Is there also, I think we run with the free QBO and other things, but that's kind of, I don't know.
Yeah, but this is such a strong forcing in the stratosphere or mesosphere. I just wonder how much the ocean state matters. But I don't know.
But that's the only difference between them.
Or just random.
Randomness.
Yeah.
But Huntley?
Oh yeah, I have a different question. So I tried this at HU, and again, I didn't get the message across really well. So I saw the big difference in the southern hemisphere in the this is temperature, right? They all have this structure. It's a tilted structure from high altitude in the polar region downward to lower altitude in the low latitude region. Why is there such a tilt?
Oh, I think this tilt is due to this tilt in circulation. If we focus on like the like how much the changes in W star, there is a tilted structure.
So you mean the circulation itself has a tilt, so the change also has a tilt. Is that what you're saying?
Maybe I should show this page. So this tilted structure is in temperature and in circulation, and also in changes in the wave drags.
I see. Okay. Oh, thanks. Thanks.
How much changes in wave drag here? Let's see.
It's like 18 meter per second.
A second.
The change is exactly what's my seven.
Sorry, can you repeat the question?
His question was how big are the changes in the wave drag on the track?
Oh, so in the wave drag, the color bar here is 50, and the color bar here is 8. So 8 out of 50-ish. 16%.
Oh. Thank you.
But if there's no more questions, thank you again.
Thank
And next presentation is given by Valeria Udin, and he'll talk about gravity waves and the FP3 based models extended into mesosphere and thermosphere.
I cannot do it from my.
No, I think you can use this one.
I was trying to check, but
slides.
it doesn't work for some reason.
I think we did this.
Yeah, you can just use
Okay.
your mouse and then, if you don't mind. You can just- I can also move.
Just would like today to talk about gravity waves parameterized and resolved in UFO3-based models extended into mesosphere and the thermosphere. And also, when I prepared the talk, I just think about that I need also to mention what we're doing in the mid and low stratosphere. How we do with basically serial KBO, etc. in the numerical weather prediction models oriented probably on short term and now for seasonal to subseasonal prediction and how we do in terms of these features. So here in the middle of the panel, you can see the slide, which is I borrow from Lucas Harris. He's basically now chief of GPDL group for dynamical core development of finite volume family models on the cube sphere. So he put that this dynamical core is very popular, and between you have NASA, GML at Goddard Space Flight Center, you have of course a GPDL family, different models. You have NCAR, but not so much because you have dynamical core, but you don't use this. And one of attractive feature, and of course you have in Vano and WS. This is the amazing dynamical core of National Weather Service podcast. And the attraction of this model, dynamical core, is also it's allowed to do refinement from the global model to the regional. And this is probably one interesting feature for gravity waves when you would like to resolve gravity waves on the 10 kilometers. So you have global simulation. 10 kilometers can go to 1 kilometer simulation for interesting gravity wave effect. So just one feature, if you don't have stationary gravity waves, 10 years of operational model give you tropical zonal wind like this, you see adjustment. This is basically a FFGFS with non-stationary gravity waves, which is we put recently, and this is mirror to simulation. So this is very much important piece of parameterization to produce seasonal to seasonal predictions. So here I just would like to tell you what current version of NOAA UFS iteration model is 16 iterations since March 2021, has 127 layers from the surface to 80 kilometers, 90 levels this model has in the troposphere. I don't know why, but so this is how it's set up now. It has 12.5 kilometer horizontal resolution globally, and currently use my unified gravity wave parameterization version 1, which has some drawbacks. And recent years I refined this, and all these pictures will be shown with revised gravity wave. We have also extension, whole atmosphere model, which is running by Ccwg, which is physics-based model, but this model now relied on the spectral dynamical core. It's totally 600 kilometers. Current resolution of this model spectral 254, 70 kilometers, 50 kilometers roughly in the horizontal space. And we under development have one with refined working dynamical core, which is replaced occasionally a spectral dynamical core. And I will show some basically results in the end of this talk with this model, how to resolve gravity waves. So, as I told you, this model version is the current operational model can unfortunately produce QBO, CEO, and connection of QBO and polar vortex. LAM-IP is also failed to drive gravity wave tidal interaction and has some shortcomings in the MLT. And so this is basically a review how we change gravity wave physics in this current version model. Basically, the major upgrade was related to the source. The source what we use currently in operation, this is MERA-2 source developed by Andrea Mollet in 2015, which is basically zonal mean vertical momentum flux with intense equatorial forcing derive QBO and CAO. So for this particular version 1, I decided not to do physics-based steering, like you do in vacuum. I put basically 2 years of high resolution, 384 and 768 simulation 12.5 and 25 kilometers, and derive resolve gravity wave fluxes from the wave number 40 to truncation, and do it for each month. And somehow I come up to seasonal variability of a gravity wave forcing. And this is illustrate how we do with resolve gravity wave forcing. With January, with July, you can sense changes of gravity wave forcing, resolve gravity wave forcing. And what we did, we just do lookup tables for the tropospheric for each month. And we just decided to use this forcing to replicate the seasonality of gravity wave fluxes in the stratospheric list. You can see basically how this model can reproduce on different height. This is 25 kilometer resolution model, right column, left column, and the left. Apologies. And the left column basically reproduce Hurdle's insider. So you can see seasonality is quite good. That's why we decided basically to use this function. So, and this is basically illustration. This is selected 5 years in a row of the narrow top and GFS with updated gravity wave parameterization. You can see we have actually decent agreement of seasonality of the zonal winds. I don't show temperature. And if you look at the particular zonal structure, so you can see mirror 2 and GEOs on the top, and on the bottom you have the prediction of operational model of wave 5 kilometers with gravity waves, and this is URAC. So in principle, we can basically use it. We still need use to gravity waves, even with high resolution models. And if you go to the tropics, so you can see basically, so we can start to reproduce the MERA2 QBO and CAO features. On the top, you have MERA2 2010, 2019, selected errors years, 2 years in a row to show you QBO in the right column, and you can see with version 1 gravity wave physics can decent prediction of the QBO. Same, we have also reproduced, even by this QBO-based circulation, we can reproduce anomalies of ozone. So, but the most important part, why we need this QBO in this iterational model, we would like to replicate basically teleconnection between the equatorial region and strength of a polar vortex. And this runs basically illustrate that now this iterational model driven by gravity wave physics in the equatorial region can reproduce decent weak and strong polar vortex for easterly and westerly phases of QBO. The prediction of the model on the left, the MERA2 on the right. So switching gear to CAO, semi-annual oscillation, you can see basically that again, the prediction in the bottom row by the free GFS, and you can see for different phases QBO, the easterly and westerly, you have simulation of strength of a semi-annual oscillation at the equator, which is basically what N. Smith basically published analyzing the Cesm data. And if you look at the driving of this semi-annual oscillation, again, if you don't get gravity waves, you have bizarre semi-annual oscillation in the top region. If you put gravity waves, so you can basically have different prediction comparing to the MERA2, and basically major impact due to gravity wave physics. Unfortunately, no gravity wave physics can impact on the seasonality of behavior of semi-annual oscillation, because above 65 you have sponge layer, and this feature basically drop down influence of gravity waves. You can see gravity waves forcing and amplify at the top, but you don't see amplification in the zonal winds behavior. So switching gear to the whole atmosphere simulation. So the current version of SWIPC model doesn't have non-stationary gravity waves. And so as a result, you can see basically running this model. I run this model, but nudge to MERA2 below 40 kilometers. That's why you have perfect simulation of the seasonality of the zonal wind at 45 south, which is compared with MERA2 in both simulation of the one, deep out and deep gravity waves. And you can see how basically stratospheric jet goes up to 140 kilometers. So, and also if you don't have this non-stationary gravity waves, so the temperature seasonality looks a little bit weird. So your minimum temperature oscillation at the 55 north, for instance, is 15 kilometers up comparing what observed by Cyber and MLS. So we're quite glad that we can have now non-stationary gravity wave physics in the operational model, and we basically hope that next versions of this model will be running with upgrades of gravity wave physics. But now I'm switching gear to the gravity wave resolving simulation. And again, I told you before, we have currently in operation one with spectral resolution 254.50 kilometers with for 2000 to 23. And Garima Malhort basically published diagnostics of resolved gravity waves from this run. And the major feature what she found when in the atmosphere, she found the four big structure of gravity wave activity around 250, 400 kilometers, which is basically orbital heights of GRACE and GOSI data, which measure temperature and the atmospheric winds. So basically here I just put the global kinetic energy spectra for 65 kilometers from different models, which is I was working with this water observing system model in the blue, MERA2 in the yellow, WAM-T62 previous configuration black, WAM-254 is red, and vacuum max 1 degree resolution is greenish white. And so you can see basically this model can resolve the part of a -5 field spectra quite nice, but -5 field spectra probably is not good resolve except only GEOS 5 forward model processing, which has some updates in the analysis scheme, which is allowed to better resolve nanoscale gravity wave activity. The operational model, if you can see, can produce at 12.5 kilometers and 25 kilometers, very nice feature of -5 field tails at different heights. I put here 100 hectopascal, but it's up to the sponge layer. And so the basic idea and challenge for us is resolve to gravity waves from wave number 100 to the spectral truncation. And the reason why I basically highlight this feature because was recent papers written by Wawg et al. With my known colleagues, which shows that all reanalysis has feature, undesirable feature, above the spectral number 100, they could not reproduce the mesoscale gravity wave activity. You can see drop off the curves from the wave number 100. So it means that analysis can degrade, even high resolution analysis can degrade mesoscale gravity waves. And this will be a main challenge for the next decade. We need to update the analysis and start to ingest gravity wave information if we have appropriate observations. I would like to highlight that Eric Becker in 2021 already recognized this before basically with plots. He do a spectral nudging in his high MCM model with MERA2 from up to wave number 32 only. And you can see when he do nudging, he can still preserve gravity wave features similar to ions. But MERA2 itself doesn't have the small scale features. So I will skip this slide probably and go how we started also to think about how to resolve gravity waves and the free waves models better. And so what we do, we started to put, especially for whole atmosphere model development. In the thermosphere, molecular viscosity and eddy heat conduction is very fast processes. It's time scale comparable to the acoustic time step of with free waves models. And our VDL folks has decided also to put some part of physics inside the dynamical core. And currently, what we are doing, we're doing the same things, but for upper portion of the whole atmosphere model. So we will be putting the gravity wave physics and 3D molecular and eddy momentum, heat and conduction inside the dynamical core. And I would like to show you first results for this model, which is run FF31, which is run from the surface up to 600 kilometers. And you can see basically a movie which is Hanli showed 2014 with a vertical wind, and this is 1 hour cadence, and you can see basically concentric gravity wave activity at 87 kilometers. This is the height of atmospheric wave experiment, which will be observing gravity waves from 30 kilometers to 300 kilometers. And this, yes, I will be finishing soon. And this will be basically probably one most interesting challenges and development of, and to bring operational models to accept the new gravity wave related missions. In next years, we will have 4 missions for this. It will be atmospheric wave experiment on International Space Station. It will be Dynagla, 2 CUBE satellites headed by LASP, and will be easy missions. And it's also mass missions, which is measure gravity waves in the stratosphere.
Okay, we need to stop, I think. Can you wrap up?
All right, thank you. So this is basically the last slide, which is I show Hanli and Julia discuss with basically behavior of the tube. And so I decided to prepare also tube how with FF1 25 kilometers can reproduce with tube. This is model without gravity wave physics. This is model with gravity wave physics. And you can see differences in the result of gravity wave forcing between 100 kilometers and 25 kilometers. It's roughly order.
Thanks. Okay.
Right.
So I guess.
I have a quick question. So on the last slide, before that, the spectrum, it's interesting to see that earlier you showed some other model simulations with 25, higher resolution. I forgot exactly what are the resolution. But if you compare the spectrum between the 25 kilometer and 12 kilometer, they diverge very far, in the small, large scales, right?
Yeah,
So they don't overlap till the.
yeah, this is a good question. Yes, this is a good question. Our 12.5 kilometers is still unstable, and so I think this is premature to.
So maybe from, okay,
Yeah,
I see.
that's why I only show 25 kilometers.
I see.
Here I just put that capability that it can extend to the spectral range what will be measured by Hanli.
Okay, right, because the blue is.
Yeah, this is very valid question. This is just illustration when enhanced resolution. So enhanced resolution simulation and with height can capture a lot of mesoscale gravity wave activity, which is beyond -5 but indeed they differ from each other.
Right, okay.
Thank you.
Thank you. Thank you for letting me talk so much.
Almost.
Next speaker
Not
is
quite as
Habib
much as you wanted.
Robin, and he will talk about the gravity wave.
Yes. Really, this. think the high resolution is really what's driving the waves.
Yeah.
We need the high resolution somehow, but we can't afford it. Thank you. Yeah, please go.
Yeah, hello everyone. I'm Hamid Pahlavan. I'm a postdoc at Northwest Research Associates. I'm also going to talk about gravity waves, but a little bit different. So, like, using machine learning to emulate gravity waves. So this work is part of a collaborative project for different institutes, NYU, NWRA, Rice, and Stanford. And the project itself is called DataWave. And it is funded by NSF and Schmidt Science. And the idea is to use high fidelity data either from observation or high resolution simulations, and some of the recent techniques from machine learning community to develop data-driven gravity wave parameterization and to overcome some of the challenges that we already know that physics-based gravity wave parameterization have. But these data-driven gravity wave parameterization come with their own challenges, including data imbalance, uncertainty quantification, and generalization. And in this presentation, I'm going to use vacuum data to actually find solutions for these challenges. In particular, we use the emulation of the gravity wave parameterization in vacuum as a test bed to address these challenges. As you know, gravity wave parameterization in vacuum is kind of state of the art and complex, and vacuum use like convective, frontal, and orographic gravity waves, and like latitude and longitude map of them for JJA and DJF are shown here. In particular, I want to emphasize that both convection and frontal gravity waves are also sourced to their coupled to their sources in the vacuum, and so which makes them even more complex and more realistic. And this makes actually emulation of the gravity wave parameterization in vacuum a more challenging task, and as such is a suitable case for addressing the challenges that I mentioned. When I say emulation, and we are going to emulate the gravity wave parameterization in vacuum, I simply mean that we are going to use input and output data from the gravity wave parameterization scheme, like the physics-based, and train a neural network. And we can use different architecture for this task. In this work, we are simply using a fully connected neural network. And then we are using, as I said, the same input and output of the gravity wave, like the physics-based gravity wave parameterization to train this model. And so, for example, the input to this neural net and also the input to the gravity wave, like the physics-based gravity wave parameterization, are like zonal wind, meridional wind, and temperature at 70 vertical levels. And then they have different sources, like the convective gravity wave have like the diabatic heating as an input, and the frontal gravity wave as frontogenesis. And then we have like topography variables for orographic gravity waves. And then they all go as input to the this neural network, and the output is like the zonal and meridional gravity wave drag. And we use the same structure, but we train 3 different neural networks for each of these gravity wave parameters. So that means one for convective, one for frontal, and one for orographic gravity waves. And when I say training a neural network, I simply mean minimizing a loss function. Here we are using a mean squared loss function, and the input of this neural network, as I said, they are like the XI, this vectorized input that goes to this neural net, and the output is the meridional gravity wave drag. And then by minimizing this loss function, we find these parameters, theta, which are the weights and biases of this neural network. And then this is the training process of this. And then this means we find a nonlinear map from the input to the output, and then going from these result processes to the gravity wave drag. So the first challenge that I'm going to talk about is the data imbalance, and this is a very well-known problem in the machine learning literature. And so And as I mentioned, the gravity wave drag in vacuum are directly linked to their sources. That means we have in a green point, we have a convective gravity wave drag when there is a convection in that green point. And these two maps show the occurrence frequency of non-zero gravity wave drag in vacuum based on average of 6 years. And then if you look at these numbers, on average, only 8% of all of the columns have non-zero gravity wave drag, which means 92% of the columns that we have zero gravity wave drag. The profile is all zero. And which results in a very imbalanced data set for training a neural network. But there are also some other problems which are specific to the gravity wave drag. So this is, for example, like one sample profile of a convective gravity wave drag from a non-zero column. And I'd like to draw your attention to this black line, which is basically the outcome of the vacuum, the output of the vacuum convective gravity wave drag scheme. And then you can see even in this profile, there are many levels. Most of the levels in the column are actually with zero gravity wave drag, and only the gravity wave drag are concentrated and amplified in the highest levels of the model, which again makes the emulation and training a neural network even more complicated. That means if we just use the common practices from the machine learning community and simply train a neural network, we do not get impressive results. So one thing that is common for training a neural network, you usually normalize your data, both input and output, meaning because you're going to give the same weight to them. And by normalizing, you usually remove the mean and divide by standard deviation. So as shown here, I'm showing, for example, for you, but you do this for all of the variables that you have. And then when we train the model, so this is the result. So this is the left panel is a 2D histogram. So this is the truth values and this is the prediction. And our R squared is around 0.5. And then we can also look at the PDF here. The black line is the truth and the dashed blue line is predicted with a neural network. And then you can see there is a huge gap between them. And if you look at for example, at the tails of this PDF, about the capturing the extreme values, we can see actually the R squared is 0.18, which is actually not good. But if we think more about the physics of the gravity wave, and then we come up with some normalization idea to actually keep the structure of the profile the same, and use another kind of normalization by not removing the mean and only by dividing by max of the standard deviation in each column. That means that we are not giving the same weight to all of the columns. So the overall structure of the vertical profile remains the same. And we do that only for the velocities for U and V and for the gravity wave drag profile. And that improves the performance of the neural net a lot. But still, we can see there are many zero values into this 2D histogram. And then to address this issue, we use a resampling method, which is a well-established practice in the machine learning community. And the idea is to actually balance your data set. So here we limit the number of zero gravity wave drag profiles to match the number of non-zero gravity wave drag profiles. And then the top panels I already showed you in the previous slide, and we go from this performance to the bottom panel. So the R squared increasing from 0.85 to 0.93. And then also if we look at the tails of the PDF, there is also improvement. So that way, and the result I'm showing here is only for the convective gravity wave drag. The same story holds true for frontal gravity wave drags, and it's even much more complicated for orographic gravity waves. And I included one slide at the end about orographic gravity waves. So that was the data imbalance issue. The other issue that we are interested in exploring using vacuum data is that the result I showed you so far are based on deterministic neural network. That means this neural network cannot predict like uncertainty quantification related to their prediction, but we need that sort of uncertainty quantification, because in practice you don't know how accurate, when you don't know the truth, you don't know how accurate the output of your neural network is. So you need some sort of metric to trust or not trust the output of your neural net. And there are different ways to come up with uncertainty quantification. Here I'm using like the three most common method that have been using in a machine learning community, and I don't have much time to go through the details, but basically I'm using like a Bayesian neural network and a dropout neural network and a variational autoencoder, and they are all use different methods to produce actually a uncertainty quantification. And the idea is that you want a well-calibrated uncertainty quantification, which means you want to have, when your model is not accurate enough, you want a wide confidence interval, and on the other hand, when your model is accurate enough, you want a very narrow confidence interval. And this kind of shown here, this kind of relationship when there is an accurate prediction of the output of the, I'm showing the Bayesian neural net. The output of the your neural net is accurate, so the confidence interval is much smaller. The same holds true for the other method as well. And then we can also look at the spread skill plot and showing like an average of 60,000 profiles here. And then the idea here is that the one-to-one line is the perfect spread skill. And then you want that your output of the model be close to this one-to-one line. And in general, all of the three methods are actually doing pretty well, and then there are not much of a difference between them. Also, they are using very different methods to provide the uncertainty quantification. The other problem of the neural networks and the machine learning in general is that they lack the ability of generalization, which means when you train them based on one system, they do not transfer the ability to another system. For example, if you train something based on the current climate, it usually do not transfer to the future climate with the climate warming scenario. And it's actually shown here. So the left panel I already showed you. This is our, again, deterministic neural network. And then this is trained and tested based on the current climate. But when we go to like a 4 times CO2 climate, so it's a climate warming scenario, you can see actually the performance decreases, both in general, but also at the tails. One method to address this is actually using transfer learning, and that's using a very small data set from your different system, for example, from your future climate scenario, and retrain part of your neural network that is already trained in your base system. And here we use just 1% of the training from a future climate, and then retrain the first hidden layer of the neural network. And then you can see actually the improvement in the performance, both in general and also at the tails of the PDF. But the tails is not the performance is not very well yet. And then for addressing this, we can also use more data, or we can use like a more clever, perhaps, loss function, like a weighted loss function, which gives more weights to the extreme events. And that actually improves the performance at the tails, going from 0.49 to 0.68. As I said,
1 minute.
1 minute. Yeah, 1 minute. As I said, the orographic gravity waves actually have more problem of the data imbalance. We also had come up with some idea, and then we were able to address this data imbalance in the orographic gravity waves. So again, this is the resampling, but going from the R squared of 0.2 to 0.8, again with the resampling. But this is like kind of the first successful emulation of orographic gravity waves. And so I will go back to this slide, but we are using these lessons that we learned from the emulation work to actually use them to develop data-driven gravity wave parameterization, but using data from high-resolution simulation. So here we are using Wawg, and then we are sampling different regions and different phases of the QBO and different regimes, and we are using that lessons actually, and using this data to develop this data-driven gravity wave parameterization. And with that, I'll go back here, and thank you.
Any questions?
Thank you for nice talk, Kevin. So, for graphic gravity waves, you have similar problem like IFS have emulation of gravity wave impact, right? Because I read.
Yes, yes.
And could you just a little bit open why is that?
Yeah, as I mentioned, the main problem is again this data imbalance, but this is much more complicated for orographic gravity waves. The first thing is that you have the orographic gravity waves only over land and not over ocean. But even if you look at the over land, and then we did some clustering analysis, and then when you do this clustering, and then you get 98% of your data having in this cluster, which is 2 orders of magnitude smaller, like the value, the magnitude of the gravity wave drag itself, is smaller than the other cluster.
Does it related to something like mountain blocking or turbulence mountain stress? What we need also to include? No, it's just you do emulation, right?
Here, the purpose is just emulation. So we are not addressing what is missing in the model itself. Probably many things are missing in the model. But even for the emulation, so we had a very hard time, and then we had to re-imbalance data to have like the same, again, balance between large amplitude events and small amplitude events, which are much more common. And then with that, we could actually get this performance. Yes, thank you.
Question. How much does the sort of training depend on what parameter you set for the gravity waves? So like if you change the gravity wave parameterization, would you need to retrain your neural network to emulate it with different parameter? Or would you do this, like have to do this transfer learning approach?
You mean like a different kind of gravity parameter? You mean from convection to frontal, or you mean?
So like the tuning of the gravity wave parameterization, if you changed it, would it basically create a problem for your neural network?
So could you apply, for instance, if you train for vacuum gravity wave parameterization something, could you apply with system to another sort of gravity wave parameterization?
Okay, probably not. Probably because there are some, they are different, and so even So but as I mentioned, the idea is not having a gravity vacuum. So the world just was a test bed to explore some ideas. But even here, if you have like a perfect emulator, probably you need to recalibrate it when you're using a different model.
So people are adding in the parameter into the input to the neural network, not for this parameterization, but like, so then you can still tune the same parameter that you would tune in the reference scheme, just in the emulated version. So it emulates both the sensitivity, but also the sensitivity for that parameter, the reference scheme.
And quick question: how different you guys doing? What Espinosa, whatever?
Ali, you're the next.
Previous report in New York was Espinosa was doing also something.
You want to set up in the meantime?
How you related?
You can continue the discussion.
Maybe it's
Yeah, sure. They are actually very close. So I mean, what we're doing here.
Yeah, I think. Okay. Thank you.
Try to keep us along. Because the discussions are good, but
Okay.
I can give you, if you want, if speakers want, I can give a 2-minute early.
Sure, yeah.
Something like
Yeah,
that.
please. I may have more slides than I need.
So after 12 minutes, I let you know, you have, 3 more minutes. It would include the discussion. Okay,
Yeah.
after 12 minutes, Alex.
Okay.
Then you have a minute or two to wrap up.
The next speaker is Hanli, and he will talk about the WACMX nature run.
Thanks. As advertised yesterday, I'll talk about the nature run. And first I want to thank co-authors Peter Larson, Francis Ditt, Kevin Fan, and Joe McInerney. And I'm told by Peter that I should prepare for some flowers. So here you are. Happy Valentine's Day. And so this is an outline I will talk about. I think I will skip most of the first few slides because I already described the model yesterday. And then for the results, we'll assess the climatology and weather, focusing on the gravity wave distribution, tides, and especially for DW1 tidal wave breaking. Rolando has some recent work, so we want to look at that. And also, because we're at the equator, we want to look at the SAO. And then we're going to look at the dynamics and composition, both in the thermosphere for O2 and 2 and MLT region nitric oxide. And then look at the ionosphere TIDs, storm time responses. Here are all things that we do not really do very well with the coarse resolution model. So we want to see what kind of progress we're making with the high res. So this is the model description, and as I said, I think I'll skip most of this just to point out this is the new SE dynamical core and the species-dependent SE core, and this is also part of the SEMA geospace development. And for the high res, we're doing the 25 kilometer horizontal and 1/10 of scale height in the vertical. And these are the nature run results where this is a solar moderate condition. And for monthly output, we have the key quantities for the composition, energetics, dynamics, and electrodynamics from the troposphere all the way to the thermosphere and ionosphere. And also we have daily output, and the daily output is mainly for tides, the major tidal components. And a subset of the monthly output are also put in 6 hourly output so that we can have diagnostics of dynamics and electrodynamics and transport. And for 2D fields, especially for those ionosphere, some of the ionosphere quantities, we have every time step 5-minute output, and we have some restarts that we can do branch runs, and this is supported by the SEMA NSC, the NCAR strategic capability allocation, and it costs about 15 million hours for 1 year. That's that's very relevant for the project, right? It's supposed to run above 10 million hours. So yesterday, John, or on Monday, John asked a very valid question. How do we know that we are resolving the waves correctly? Because we do have artificial damping, things like that. Are we doing a good job at all, or are we resolving the right gravity waves? So here, the first thing is we want to look at the gravity wave distribution, latitude, height, and latitude, longitude, and over height, and try to compare that with available observations. So here are looking at the variance. The gravity wave in terms of temperature variance for 4 different heights. This is tropopause, stratosphere, MLT region, and the upper thermosphere. And then for the tropopause, we're comparing this with a recent study by Randall et al. Looking at cosmic 2. And here they're also looking at this is temperature residual variance. And if you look at the distribution, first at the equatorial band, you see the activity in the Western Central Pacific, and which is captured by the model. And then the western part of South America and the western part of Africa. And both does show, both do show the activity, heightened activity in the model. And then in the northern hemisphere, mid-latitude, you see this increased activity downstream of the Tibetan Plateau, and you do see some of that in the model, and then in the Rockies. And then this is a look at the stratosphere, for January, and we're comparing with Sabre. And Sabre has a Atlantic center view, and we have a Pacific center view. So there's a 180-degree shift. So I'm using the pointers to connect the different activity centers. But basically, you see this, the equatorial band propagates forward a little bit, which we understand is due to the wind system. But the activity center do correspond quite well. And then in the northern hemisphere, there's an activity center between or extending from east part of North America across the Atlantic to western part of Europe. And that's likely due to polar jets, polar vortex, and it is indeed captured, captured by model. Here's the observation results. And then when you get to the MLT region, the distribution of the waves become more uniform, likely because of the propagation and probably also regeneration, secondary waves, and further poleward shift of the southern hemisphere band, and that's captured. And then you still have the signature from the waves from polar vortex, and that's there. And if you go to the upper thermosphere, this is CHAMP results, and you see this middle high latitude band in both hemispheres. We, at least qualitatively, we capture that. And the peak activity are at both geomagnetic poles, and both are captured by the model quite well. And also, if we look at the contribution, the scale dependence of the wave momentum flux, we see that this is a percentage contribution from large scale waves and from smaller scale waves. This is latitude and height. And you can see that in the middle atmosphere, the small scale wave play a critical role, as can be over a mid-high latitude, especially in the winter time, can be over 90% contribution. Even in the thermosphere, you still have a very large contribution, like 60% or larger. Just want to point out, this is the altitude where all is making a measurement. And you can see that this is a region where a lot of wave activity is, a smaller wave activity is making important contribution. And this is exactly the range all is measuring. And then we look at the tides. This is if we look at the lower panel, here is Rolando's results from Sabre analysis for a full year. And this is the DW1, the migrating diurnal tide. And you can see the peak, in the March peak, has an amplitude at the equator of about 20K. And if we look at the regular resolution Wawg model, we generally underestimate that peak. Here the contour lines are the magnitude, and the colors are the standard deviation. So this is a variability. So you can see that here is like 15K probably. And but with the high resolution model, we do capture that larger amplitude. And as a result of that, we can do a better job in capturing the tidal wave break-in. This is again from Rolando's paper, 2023 paper, and he was showing the overturning of the potential temperature by the tide, DW1. And for the model, we do have an upper limit, stability limit, so that we can not go too far beyond the overturning, but you can see the steepening of the potential temperature is pretty well captured. And then this is at the equator, but looking at the mean wind, semi-annual oscillation. In the parameterized, low resolution version, the parameterized wave does drive a SAO, but the structure, especially the phase structure, it doesn't look right compared with observations. And now with the high resolution, the SAO structure looks much better. The strength is a little bit maybe larger than observations, than climatology, but the structure in general looks pretty good. And then we look at the wave impact, thermosphere. In the thermosphere, this is looking at the result waves. So here's the zonal mean zonal forcing with scales less than 2,000 kilometers. So it's mainly gravity wave, result gravity wave for January. So maybe you can focus on the two large eastward forcings in the middle upper thermosphere. And they are very significant, they're over 100 meters per second per day. And also, if you look at the Mariana wind, the Mariana forcing is also quite large. What they do then is they change the circulation. So here we are comparing the solid line, which is the high resolution, the residual circulation from the high resolution in northern hemisphere and the southern hemisphere. This is the meridional component. This is the vertical component. And you can see that with the gravity wave, a result gravity wave forcing, in the northern hemisphere, the mean circulation is slowed down, while in the southern hemisphere, it's actually strengthened a little bit. And same thing, you can see that in the northern hemisphere. So the downward circulation is really weakened here. What that does is that it would change the composition. So it would decrease the downward transport of atomic oxygen, and at the same time enhance the upward transport of the or the mixing of the molecular species. And in earlier, coarse resolution simulations, we always overestimate the thermosphere O2 N2 ratio, and this is O2 N2 ratio as function of latitude. And now, and the red here is the GUVI observation of O2 N2 ratio. Now with the high resolution, we're doing a much better job in getting, in comparing the observation results.
You're 12 minutes now.
Okay, I'll just quickly go through some of the remaining slides. And then, this is nitric oxide in MLT region. That's always a problem because we are underestimating the O2 N2. Sorry, nitric oxide there, but especially in the polar night jet or polar night vortex, and then in high resolution now we're doing much better, and you can see this is one day, this is multiple for 4 months, and clearly we're having a much stronger or larger nitric oxide there. So I'll just quickly, just mention that now we can, with this resolution, we can resolve TADs and TIDs in the thermosphere and ionosphere. And some of the comparisons with some of the older statistics, they look reasonable. And maybe I will just skip this slide. These are storm time studies. Just want to show that they capture some of the structure, for example, time of ionization and the nighttime enhancement during storm time much better in the high resolution model. And just some potential applications with the high res, just use that as a virtual lab to do various things. And again, I voiced my concern over Globus, and I need to find the right people because I did send a Cesm help and still, they haven't got it fixed yet. But yeah, that's the problem.
Question online. John, can you unmute yourself? We cannot see the chat, else we have to stop the sharing.
Yeah, hi, thanks, Hanli. It's an impressive modeling feat that you just described, really.
Yeah.
I just wanted to ask if you had an estimate for the effective horizontal resolution of this 1/4 degree SE system that you just described, meaning the smallest wavelength that is resolved without excessive damping. And it's usually described in terms of a number of grid points, like 7 delta X for WRF, according to Skamrock's work, for example. Do you have a number like that for this nature run?
Yeah, it's we looked at the spectral structure, and you can see where it's has start to have this sharp drop, and it's around somewhere between 200 to 250 kilometers. So it's maybe 7 to 10 delta, somewhere maybe 7, 8, 9 delta. Yeah.
Yeah. What chemistry are you? Oh, sorry.
I don't know.
Sorry.
Do you have a middle atmosphere chemistry mechanism?
Yeah, that's
in
a
this?
MA chemistry.
Yeah,
Yeah,
okay.
yeah, that's right.
It'd be really interesting to look at the waves and how they affect polar chemistry down.
Yeah, I mean, I can.
We've looked at this a little bit, so.
Okay.
Because the amplitude will, plus or minus 10 degrees in places that really is gonna
Yeah,
drive
that's right.
heterogeneous chemistry, so. I'll
Yeah,
talk
yeah,
to you.
yeah, for sure. You don't use Global, so you're okay.
Good.
A very
Oh,
good question.
Basically, you have one run, you switch off all gravity waves except paragraphic. Or
Everything.
Everything.
Since this round, we
Yeah,
switched
everything.
off everything.
So my question is basically, you know that QBO can influence tides a lot.
Yeah, that's right.
So if you don't have basically gravity waves, so I have some concerns that it will support with QBO-like features.
Right.
So, and at least we need to think about how to handle this, because according to my understanding and data, approximately 100% differences in the diurnal tide amplitudes at around 100 kilometers. So
I see.
when we do nature runs, perhaps we need to do at least 2 years runs for Aussies to get strong tides and weak tides.
Right. Actually, I think in this case, you can treat it as, I think it's just the westerly phase.
Westerly.
So you can treat it as a westerly phase of the QPO. Yeah.
But excellent issue.
Okay, thank you, Hanli. So first, we apologize. The agenda was updated kind of last minute, and I think we sent to a speaker, but the one posted online was still not correct. So Ben, hopefully you knew that your talk was at the break, not before. So we apologize for that. And the last speaker before we'll have a break is Natalie Wawg. And we are sharing the slides here, and you can just tell us when to go to the next slide. So sorry again for everyone. Hopefully it was not too much confusion.
Can you hear me okay?
Yep.
Oh, good. Well, thank you so much for sneaking me in here. My problem is I'm remote and I'm in Europe, so they snuck me in a little bit early. You guys are going to have to come down to earth a little bit. We're going to talk about surface concentrations here for this. So I'm presenting a recent paper that we submitted to Earth System Science Data. And it's AeroMap. It's a new data compilation and modeling approach to understand the fine and coarse mode aerosol composition at the surface. And you can see there's a lot of co-authors. We've combined a lot of data that people had somewhere to try to create the most comprehensive particulate matter aerosol database that we could. It's about 14,000 stations, over 20 million observations. And importantly, it includes not just the data in the US and Europe, which is usually what are used in multi-model comparisons or model comparisons, but a lot more data, say in Asia, we have Chile, Australia, South African data, Turkey, and Israel in this data set. So I'm just going to briefly describe it. For the plots I show here, we grid everything to 2 by 2 so that you can see something. Otherwise, they're just dots. In the places that are covered, they're over covered, and the places that aren't covered are poorly covered. Let's see. So next slide. I'm trying to advance it from here. It doesn't work. I think everybody knows that aerosols are really important for understanding climate, that they're the largest source of uncertainty for the current radiative forcing and therefore for climate sensitivity. And the different aerosol sources have a very, very different trends going in the future. Sulfate should drop off if we succeed getting off fossil fuels, but the nitrogen aerosols, for example, nitrates and ammonia, probably will stay steady or go up as we intensify agriculture. So so different trends depending on what the composition is, and then of course they have different impacts as well. Some are absorbing versus reflecting, and you simply can't get that information from remote sensing. Next, please. Very briefly, we compiled a whole bunch of daily to weekly aerosol data, everything we could get our hands on. And this first paper is just showing the annual mean. Next will be temporal resolution and different time periods and trends. We compared to the CESM, the default version of it, but then added a few things. For example, the nitrite and ammonia from the Viridal study, as well as agricultural dust, road dust, and some other sources that were lying around. The most important are that we added the nitrogen aerosols and the agricultural dust, as we'll talk about later. And then we also propose a methodology to compare all the different compositions in the model to available observations that seems reasonable and means that we can actually check the chemical composition, or if the simulation isn't just getting the total, but actually the chemical composition correct. Next slide. Here's just an example. This is the PM 2.5 total mass here, just to illustrate, you have really good coverage over the US and Europe. And now, we have the data from Asia, China, and India also included, as well as, like I said, we have the Australian, the New Zealand, the South African, Chile, and a few other countries added. The top scatter plot shows when you grid everything to 2 by 2, you have 742 grid boxes, but this actually includes over 7,000 individual stations, each with between 10 to thousands of data points. One trend that you can kind of see here, but actually let's go to the next slide. We'll talk about it there. And perhaps the model is too high over Asia. This is using data that people don't normally use because it's not easily accessible. But you can see in the scatter plot, you see a little bit the model is too high over Asia specifically, and then you can see in the comparison there that it's pretty widespread over large parts. Is this because of the new data, or is it because the model is really actually too high over Asia? Now, I should also point out that the time periods, we're not being careful about the time periods here, so that could explain some of this as well. We're using, the mean over the whole time period versus model output for, 2012 to 2014. Actually 2013, no, 2012 and 2015, so 3-year average. But the bottom right shows a comparison. The U.S. Embassy has sites, and you can see, I'm afraid that the very bottom scatter plot, the bottom fell off, but that's what is shown from the U.S. Embassy sites there. And then compared to, say, the Chinese air quality stations within 1 degree or the Indian stations within 1 degree. And you can see that perhaps the new stations that we added are actually biased low. It's a little bit unclear. So maybe these stations are not very high quality, or the representativeness of the U.S. Embassy. Anyway, we're just flagging that there's a little bit of an issue here. Next slide. Just want to point out that we have a lot of composition data then for PM 2.5. Now, the first thing is that we don't have anywhere near as much composition data as we have total mass, right? That's pretty obvious. For example, you lose China, most of China and India, and other places as soon as you go to composition. But composition is really what matters. So, how can you fix the model if you don't know exactly which part of the model is wrong? But we have, sulfate and BC, EC. You can see it's similar to what's been shown for this model, that the sulfate is a little too high in the model. Next slide. We also have OM or OC, as well as sodium measurements. Maybe it looks like the sea salts are a little too strong in the model, but then over industrialized regions, there might be a local source of sodium that we haven't included in the model. Next. Aluminum is a proxy for dust. It looks like the model is over predicting in some of the high regions there. Next. And the nitrogen aerosol. So from the Viridal study that we took these from, from a separate chem run, the nitrate was too high in those simulations. So we have it, and we can, if we have it the model values, we can match the available observations just like they found. And this is probably because the chem simulations they had did not include a thermodynamic model. But, you know, it looks like we're on the right planet for what nitrogen aerosols we're using here. Next slide. We can do the same thing for the PM10 then in the model. And again, you get a lot of coverage when you look at the total mass, or a lot more coverage than we've previously looked at. Next slide. We have perhaps a similar bias over Asia again. Next slide. And then we can again look at the composition. The model seems to overestimate the sulfate in the coarse mode. And we added black carbon to the coarse mode. Maybe we added a little bit too much based on some databases from GAIN. Next slide. And again, you know, the OCBC and these salts are available, but it looks like the OC or the OM is a little over predicted in the model. I mean, one of the things I've been interested in is whether or not we're getting, whether there's evidence for primary biogenic particles being more important. And we included pretty small primary biogenic sources of for OC and OM, and you know, evidence suggests that we're already over predicting. We don't need more there. So you know, darn, one of my hypotheses gone. Next slide. Dust again, this will be a new data set, and the model is over predicting in some regions. Next slide. Nitrates. Of course, the model doesn't differentiate between fine and coarse mode nitrates, so we're just throwing everything in there. But next slide. One of the really important points to make is, even though this data set has probably twice or 3 times as much data as the previous data sets have been used to compare to models, we're only covering about 3% of land, okay? We really need a lot more observations of aerosols in order to know what aerosols to put in the model. And you can't get composition from the remote sensing data. So just an argument that we need more in situ data. Next slide. The other thing is that we, you know, we added a whole bunch of extra aerosols to test if they were important. And you can see on the left, that's the percent of the PM 2.5 concentrations that are in the default CESM that we used. And you can see large regions of the globe are well below 70%, well below that yellow color. They're really into the blues, where we're just missing a huge amount of the mass in the default model in the PM 2.5 and the PM 10. The most important of those is the nitrogen aerosols. So I'm not saying anything new. Everybody knows that it's a really important composition of aerosols that we're missing. I just want to say it again. It's really important to have the nitrogen aerosols. We're probably missing about 30% of the aerosols, and they have different trends. Sulfate is not typical of all the aerosols. You know, nitrates will probably stay steady. We also should include agricultural dust, and so we can put that into the main version using this. Of course, to get the nitrogen aerosols right now, we'd have to run the full chem. So maybe there's an argument for trying to develop a simple nitrogen aerosol. A lot of the other additions didn't seem to matter that much. So we can add them if we want, but they're not super important. Next slide. So just to summarize, here we have a new annual compilation. It'd be great if we could get the CESM regularly compared to this. I'm happy to help make that happen, get some aerocom experiments using this. We're going to add seasonality and trends also. That'll be the next paper and data set that comes out. We include the composition data. I think that's really important. But there's not enough in situ data to constrain the current distribution of aerosols, so it's going to be really hard to understand who's causing what, and you know, how exactly we get nitrogen aerosols into the model cheaply. I think that's a really good question. We have a proposal for how to do the agricultural dust, but we're going to miss trends if we don't have those land use variables. Of course, aerosols are even more constrained if we look farther back than 1980, which is all we looked at for this study, right? We have no idea what the aerosols were in the pre-industrial time period, so you know, the uncertainty just blows up when we do that. We have an opinion article that came out on ACP on that. Thank you very much for accommodating my weird time and my extra talk here. Thank you.
Yeah, great talk and incredible data set. It seems like the elephant in the room is you're missing data sources over Africa where there's a lot of emissions. Is there a plan to increase the coverage there?
Well, that's what we're arguing for, right? Like, look at it. We need a ton more data in Africa. South America is the same way. It's possible that we missed some of the air quality data. I think there's some in Brazil and Argentina. We just couldn't figure out where it was. And a lot isn't publicly available. So there's huge gaps. Let's just put it that way. So we need to have a plan for doing that.
Yeah, so I mean, you modified the model a little bit to have nitrate included, and you also modified it to have larger aerosols. I just wonder what versions you used.
Yeah, so I used the Cesm. So the version that Longley extended to have multiple dust species, and then I threw the coarse organic and BC into those, or added those on. So I use a modified version of Longley's speciated dust scheme, if that makes sense.
Yeah, it will be interesting to explore those options too. We do have the MEM7 version has the nitrates in a simplified form, right? That is, but
Yeah,
we haven't really used it much. So it's another option maybe that could be explored. I mean, we do have the Karma version, but it doesn't have nitrates yet in the CSM version. That's another option. But many things we should maybe do a focused brainstorm there too, what we can do one day.
Yeah, well, it was a lot of work to pull together this data set. So I'm super happy to collaborate with people who have some use for this, down to the daily to weekly level. Can't publicly give it out, but we can collaboratively give it out, just because some people are very private about their data sets, basically. And you can see, it's really important to include all the people who did all the hard work to collect these data sets, and that's what we're doing here.
Yeah, that's great.
So Susan, I think online has a question.
Oh, yes. Thank you so much. And I was wondering, oops, let's see. Yeah, I was wondering, as it seems like there's a need for more, from what I've heard, more neighborhood level monitoring of pollutants such as PM 2.5. And I was wondering if those type of neighborhood like scale monitoring, if that is increased, would also benefit your acquisition of data sets for this kind of climate modeling, especially with such like terrible air pollution that we experienced last summer here in the US and Wisconsin, where I was, for example. Thank you.
Yeah, we had it terrible in Ithaca also. I think that the neighborhood level data is super important for air quality. I didn't really put together, we didn't put together this data set in such a way that it's great for air quality. Some of the data, we didn't know exactly where the station was, so we had to approximate it. And so you'd have to be a little bit careful if you wanted to do it at really fine resolution. But adding more data to it isn't too hard. But it's actually almost a little bit controversial to include urban areas in comparisons with Earth system models, right? People generally try to look at remote regions instead, which to me doesn't make sense because such a huge fraction of the land surface is actually cities. So we included them and then also gridded them to 2 by 2. But I think neighborhood level is super important for air quality considerations, especially in the developed world where you'll get neighborhood level. In the developing world, we just need any data. It doesn't really matter. We need it all.
Oh, thank you. Yeah, I was just wondering if the data, if there are more stations, if that can be added to the data sets, because
that'd be great if you know of any. One of the reasons to give this talk is to find out if there's any more data, but we've been given it for a few years, and hopefully we've got it all, but hopefully there's more data coming down the line.
Thank you.
All right. So thank all the speakers for this morning. We had originally scheduled for a 15-minute break, which was to end at 10:35 right now. Maybe we just take 10-minute break and come back at 10:45. Ben's talk will be.
What's the resolution of the horizontal? Yeah.
So coffee, I think we have to get done.
Go ahead.
The other coffee, by the other buildings. You can walk down to the.
Oh, yeah. Do you have a few chemical species you've outputted?
Yeah. I can just copy paste what's on the 6 hourly output. There's not a huge amount, but there are a few. And we can always, I mean, of course, on the monthly, there are many, but on the day, on the hourly, 6 hourly.
Yeah, let's see.
If there's something that you find interesting, say in the temperature perturbation.
Branch off and rewrite.
Yeah, we can branch off. We have.
Could you send me that list?
I saw how many, and then we'll.
Yeah, I will do that now.
We've had a project, look at growing rates.
Okay, yeah.
And, effect on chemistry, and this might be a really interesting thing.
Yeah, it's the way will be like Sean was saying, it will be a bit on the large end.
Okay.
Will resolve
Let me take over.
waves
I won't.
about 200 millimeter and larger
Yeah.
with horizontal wavelengths.
Okay.
But it will not have the super small scale, but at least it has something. You can take a look.
I'm gonna go grab a cup of coffee and I'll be right back.
Yeah, me too. Let me.
Yeah. That's really interesting.
Yeah, I think
Only for minutes. Yeah.
Do you get us something for them?
I need to do that for. I'll be talking to that judge. So hopefully at some point I'll be able to start working on it. Do you want to get coffee? Because I want to get a little bit of coffee.
Sure, yeah, you can go.
Yeah, so we can walk around. Yeah, very cool. Lots of photos.
So Sean, I mentioned to Eric Jens that you're here. And Eric said, "Oh, I'd love to see him," but I didn't know you'd be in Foothills Lab tomorrow. You might want to ask him if you can just come and say hi to you.
Wait, who?
Eric Jensen.
Oh, Eric.
Yeah.
Yeah, I might. This afternoon, I
Or
might
I
drop
can-
by there and
I can text
to
him.
see. Doesn't know. Does he still have an office at Ecom?
He does not, but he can come in for he's been coming in for coffee hour once
Oh,
in
okay.
a while. So
Yeah, because I'll be in there. I'll probably head over there this afternoon for a while, and then I'll be there all day tomorrow.
okay, that sounds good. And Eric's getting a puppy.
He's getting a puppy.
Yeah. Oh, so cute.
He's gonna be busy.
Cava Poo. Do you know Cavalier and Poodle mix?
Oh. Well,
Eric, you said?
wow.
Oh, it's older. It's just a little. So cute.
Sounds adorable. Cool. Grab some water.
Yeah, but if you take out, it isn't for, I mean, come on. See, you didn't. Are you gonna speak? So what? You know.
I see.
Or maybe Sean could take notes.
Yes.
Maybe you could take notes during the discussion session.
Yeah.
Yeah.
We can all remember what we discussed. Yeah. That's right. I like it.
Yeah. Oh, okay. Right now.
Okay, great.
So we have people online, including Ben. Do you want to come here or do you want to?
I've advancing the slide here, so.
We can see if it works. You were able to present and that should work out just fine. Change the layout again to the spotlight because I don't know why we only see our room here, but that's what it is. Yeah, should I give you a warning at 12 minutes? Like everybody, that means basically time is up, but if you go a little over, it's fine. We'll just have to do it. Try to be shorter in question.
I tried to do 12 minutes, so, but let me know if.
I tell you when it's 12 minutes and it's basically time is up, but everybody took longer, so that would be unfair. Okay, right. You're the,
Yeah, so we'll start to try to keep some sense of on time as people are coming back. So first speaker now is Ben, and he'll talk about data assimilation studies with CESM.
Thanks. Yeah, I'm Ben from Atmospheric Chemistry Observation Modeling Lab here at NCO. This is a work I've been doing with Cesm and many others. So we're using the data assimilation with such test bed that is developed at NCO also by the Cesm lab. It provides, it's a community and open source software for Ensemble DA and provides many tools that allows for efficient Ensemble DA such as localization and inflation algorithm. And we are using the setup developed by Kevin Weller, the citation here. That developed methodological data assimilation for reanalysis within the GAM plus DART, and using the EAKF and other tools for Ensemble DA. And so what we did is adding the chemistry from CamCam in the finite volume version. And as you know, it includes comprehensive gas phase chemistry and aerosols in an interactive manner as opposed to the regular CAM. And so we had perturbation to name these parameters and emissions from anthropogenic campfires to generate a 30 members that's what we can have for this chemistry of 6 hours forecast. And every 6 hours, we perform meteorological data assimilation, so changing the initial conditions of the meteorological state vector. And we add to that another state vector for chemistry, here shown for CO, where we change the CO initial conditions, which is important because CO has secondary sources in the atmosphere. And there are also transport errors and chemistry errors that would impact the CO distribution. And we also update anthropogenic and fire emission fluxes separately. So then we can scale back the daily emissions from both anthropogenic and fires for the next forecast step, and that allows dynamic adjustment of emissions without attributing too much of the errors to those fluxes, because we're also assimilating the initial conditions. So here's an example for Ccwg close to the sources. So this is one of the largest hotspots for CO emissions from anthropogenic sources in the world. We've been flying off of the outflow from East Asia and also over Seoul, one of the largest mega city in the world. And you can see pretty large levels of CO measured by the NASA DC-8 over the months of May and June 2016, with different weather regimes, dynamic, stagnant, and pollution transport. And so the assimilations of meteorology alone in blue doesn't reproduce your CO levels, and when you assimilate CO profiles from MOPIT, you improve the CO vertical distribution by quite a lot, but you still underestimate in the free troposphere. And so out of this, we can get posterior emissions, and we can see that not only the emissions are underestimated over China, there is also a very large spread between different estimates. including with other chemical reanalysis that using different models, but similar type of chemical data. So like TCR2 from. So now the global scale. Here is another DA experiment in August 2015, and you can see that when you compare the MOPIT column versus the MED DA and the MOPIT DA experiment, that we underestimate not only close to the source, but also over wide areas of the Northern Hemisphere. And so the background CO is underestimated. But on the other hand, the CO from fires is overestimated in the tropics. And after DA, you reduce those biases significantly as expected. And so to the right, you can see that the emissions increments we're getting out of this, including so from anthropogenic and fires. And we also did assimilate MODI COD, and we found that the increments on the black carbon and primary organic show similar patterns than for CO, suggesting that most of these errors are coming from the systematic errors in the emissions. Because whether you assimilate MODIS or MOPIT, you find the same increments. So another estimation of thin emissions over the tropics that led to overestimation of black carbon, organics, and CO. While we underestimate CO in East Asia also, and also in over the US and Europe. So what I did is to derive posterior emissions for the entire GAMS inventory using just that 1 month inversion. So I'm just assuming that the errors don't change over time. And so I'm changing the GAMS emissions and the FIN emissions. And I'm just running forward. So from January 1st, 2015 to January 1st, 2019, so 4 different years. And those are the differences in RMSE compared to MOPIT. So the blue means that it's better, and the yellow means that it's worse than the reference. And you can see that the anthropogenic signal propagates and improves the CO for the entire Northern Hemisphere extratropic CO, while the reduction in the Southern Hemisphere tropical CO that was peaking in August when we did the inversion improved CO at that time and propagates over the rest of the year. That strong seasonality doesn't lead to an improvement for the other fires, because we actually can see here that we're actually increasing the CO. We are increasing CO in Southeast Asia. And so we expect that the FIN emissions that peak in May would be biased high. And so since we are increasing the anthropogenic emissions, then we actually degrading the source in Southeast Asia that you can see here. But most importantly, the results in the background CO are rather small. And it's mostly over the big hotspot of emission sources that you can see changes. So what I did is to artificially reduce the JO single D, so the OH source, which correspond to a reduction of OH that would impact the CO sink. And so here you can actually then see the impact of OH, and it's actually larger than emissions. And it's showing a clear improvement in the northern extratropical CO, which means that OH is overestimated there, but is actually underestimated everywhere else. So it shows that OH and chemistry matters, and probably maybe more than emissions for CO. which is kind of expected from the COE. And so the other thing is that when you look at ATOM, which was covering 4 different seasons over a large range of latitude and altitude, and you can see the CO underestimation in northern extratropics here that is only changed a little bit when you change emissions of the OH source. So it shows that chemistry is very important there. The overestimation of thin though is much corrected in using the posterior emissions. When especially in August, which was the months that we assimilate. So we assimilate August 2015, and this is August 2016. So now a more recent paper, I've been trying to compare MOPIT and CRIS CO, so 2 different satellite instruments. And I wanted to start using the quantity conserving ensemble filter framework from Jeff Anderson within the room. If you have questions, it's got like 3 different papers. So those are part 1 and part 2. Specifically, this allows to deal with non-Gaussian and modestly nonlinear distribution for observations and the prior. And specifically here, we're using the bounded normal rank histogram, which allows to better to assimilate positive quantities, which is the case for both chemical constituents and their fluxes into the atmosphere. So here there are some differences between what CRIS and MOPIT are suggesting. CRIS actually could show a larger CO from the tropical sources. And so this disagreement is shown here by the differences between the 2 different a MOPIT one and a CRIS one. And on top of those EAKF one, I have the DNRH simulations. And so what I did is compare the RMSE from the EAKF and the BNRH when I'm assimilating CRIS versus MOPIT. And so it shows the when you assimilate CRIS on top of
12.
Yeah, just finish this quick. And so zooming in, you can see very, very large reductions compared to the control when you estimate MOPIT, but further reductions when you estimate both CRIS and MOPIT, and further even reduction when you use the BNRH instead of the EAK. So now I have new posterior emissions for this case study for May 2018. And so I used that in forward simulation, and I also added methane emissions and hydrogen chemistry. So instead of using the SNP6 methane like this, I'm using the GCP methane emissions here. So I showed that in 2020 that for the Ccwg period, it was better to do this, but then I couldn't really move forward with this because the methane lifetime is way too short in CSM. So here we take advantage of the halogen representation and we input that in the model, and we also use the posterior emissions from the BNRH, CRIS, MOPIT inversions I just showed. And now when you combine, you reduce, if you look at the top here, in the winter time, using both the combination of posterior emissions, halogen chemistry, and methane emissions, you reduce the CO biases by quite a lot, which is much better than the paper that was published last year where there was no sensitivity to J0 single D and emission. And this allows to model methane, which is going to be the case for further study and was presented yesterday by Ami. So yeah. Also been working with Wenfu on MOPIT profile and column and looking at different satellite spectral retrievals done by MOPIT, which respond to other different satellite instruments. And the papers has been accepted for publication yesterday.
Mhm.
So I'm just gonna stop there.
Thank you.
Any questions? Well, Rebecca, you go first.
Yeah, thanks, Ken. That was great. I had a question about the OH. I think you hinted at the answer there. So you said the OH was too high and too low, southern hemisphere, northern hemisphere. Why do you think that is in the model, that simulation?
I think it's related to nitrogen chemistry.
Nitrogen, okay, not the halogens?
So the nitrogen chemistry is producing, I mean, when I compare to atom, I found that nitric acid, for instance, is too high.
Okay.
So when you include the halogen chemistry, you update the nitric acid, the N2O5 photolysis on aerosols, which led to reduced nitric acid and nitrogen in general, which reduces the OH and end up increasing the CO in less than lifetime.
Okay, cool. So we should all be halogens to get the OH right.
Because I think in northern hemisphere you get way more nitrogen.
Okay.
And so that probably is the reason.
Thanks.
What is your lifetime right now with halogens?
We need to calculate that properly. With, but it's probably closer to 9 when 9.5 is the target.
Rafa, do you want to ask a question?
Yeah, nice talk, man. Can you go back to the plot of methane comparison? There's a couple of slides before that. I remember yesterday talk when you showed these profiles, there was a time series. Did the simulation run for 5 years or something like that?
Yeah, it's we do 2 year spin. It's 2 year spin up, and then this is for 3 years.
And have you checked how is this comparison for each specific year? Because I think those 5 years or those 2 years spin up for methane in particular should not be enough to get mostly in the free troposphere. You need larger spin up to get such a long-lived species. I mean, it's a short-lived or long-lived, whatever you want to call it. But you need at least, I would say, 10 years to have it respond to the changes in OH levels.
As far as tropospheric mixing, we saw that 2 years would probably be good enough. But yeah, we want to improve this setup eventually to run longer simulations. But yeah, we already did run a lot of those tests, and we could have done that if it was 10 years every single time. So that's the main reason.
Okay.
Stop sharing, then we jump in. We should probably move on.
Yeah, so thank you, Ben. We will move on. So next presentation is from Beijing on interannual variability of the stratospheric hydrogen chloride simulated with SD-WAF in recent years.
Awesome. Thank you, Nick. Thank you, Simone. And today I'll be talking about stratospheric ACL in recent years. First of all, I'd like to acknowledge my co-authors, Doug, Rolando, and Sasha here at NCAR, and Jessica New at JPL. Let's get it started. So stratospheric ACL is the main reservoir of chlorine. So monitoring its trend in the stratosphere is essential for predicting our climate as well as ozone recovery. And in the northern hemisphere mid-latitude, its variability is influenced strongly by large-scale circulation. And I want you to remember this. And in this study, we are using specified dynamics version of Wawg and the measurement from NASA's MLS satellite for about 16 years, starting from 2005. So before we look at stratospheric ACL, let's look at sources of ACL in the troposphere. So among many other sources of chlorine in the troposphere, I was told CFC11 account for about 25% of chlorine entering into the stratosphere. So as you might know already, since 1987 Montreal Protocol or early 90s, the concentration of CFC11 has been declining constantly until it stopped declining, or the rate of decline has slowed down in 2012 due to unreported production. As you can see from this figure on the left, this is from Monscott et al. 2018 paper. Red curve or line is for Northern Hemisphere and blue is for Southern Hemisphere. And the more recent update from the same group of people published paper in 2021, this is an updated figure from them showing actually an accelerated decline in the recent years, 2019 and 2020. And you might think at this point, maybe stratospheric ACL might decrease as well. Just wait. So this is what stratospheric ACL trend look like. On the figure, on the left figure is showing trend in ACL estimated from MLS satellite for 2005 to 2020. There are negative trends in the Southern Hemisphere. And also there's positive trend in the tropics and the Northern Hemisphere. As I mentioned before, this is largely influenced by the large-scale circulation. And one of the main circulation or dynamical features we are interested in is QBL. So on the figure right is showing two curves. The red curve is something called DJF shear index. What it means is in the tropics, there's monthly mean zonal wind. We take the shear between 50 to 15 hectopascal for December, January, February, which is red curve on the figure. When you overlay this curve with ACL anomalies in the Northern Hemisphere mid-latitude, specifically 35 to 55 north latitude and 30 to 70 hectopascal, they agree really well. So what it means is that the DJF shear index explains much of the dynamical variability in ACL anomalies. But pay attention to this figure. The time is from 1998 through 2014. And what happened afterwards? So the top figure is the same figure I just showed to you on a previous slide. And the bottom figure is the same figure extended up to 2012. Due to some update in the data set, they're not exactly the same. But as you can see, the relationship between DJF wind shear index and ACL anomaly holds about until 2014, when I added this gray solid line here. And after 2014, doesn't work very well anymore. For example, between 2015 and 2019, ACL and DJF shear index do not match. In 2017, there was high ACL. In 2019, low ACL. And what happened? Before we look into a more recent period, let's just look at WACM. How does WACM do with this trend? On the left is the figure, the same figure I just showed to you, ACL trend estimated from MLS. And in the middle is WACM 6 SD. The general morphology is similar, but as you can see, WACM 6 trend is a lot lower than MLS, but it's still capturing the negative trend in the Southern Hemisphere. But the positive trend in the Northern Hemisphere is almost absent, even though this trend is not so significant. And here I added one more run. This is something called WACM 6 high EESC run. What it means is we fixed the EESC boundary condition at 1998 level. So imagine that the atmosphere ACL has not been decreasing as a real world. And more interestingly, you can see this positive trend in ACL. So simple message from this figure is what's in the troposphere getting into stratosphere matters in ACL trend. So in WACM 6, maybe we're not getting enough ACL or chlorine from the troposphere entering the stratosphere. And one suspect for this recent changes in dynamical correlation between this vertical wind shear and ACL could be this disrupted QBO happened twice in the recent years. One happened in 2016, one happened in 2020. This is easy to see on the figure on the right. This figure is a time pressure plot of zonal wind in the tropics. Every 2 years or so, the westerly shear and easterly shear has been propagating downward until 2016 and 2020. Another way to look at characteristics of the QBO is using two leading EOF modes, EOF1, EOF2, between 70 to 10 hectopascal. This is how it's done in Wallace et al. In 1993 paper. As you can see from the plot on the right, each star represents each month, and the whole circle goes to counterclockwise. Every month, QBO is going down. This is looking at phase and amplitude, circulating really regular manner until the red dots are for 2016 and blue is 2020. It was disrupted, totally different. So now we know, due to this disrupted QBO, the DJF shearness was very small and ACL was acting a little bit differently. So one thing we can do is, let's look at the impact of QBO on ACL. So what you can do is make the composite average of QBO easterly versus westerly shear. So this is what I did here. There are two figures. One on the left is based on the observation, so MLS ACL. One on the right is based on Wacom 6. The colors represent ACL anomaly for QBO easterly minus QBO westerly here. I use 50 hectopascals zonal wind in the tropics. And solid or dash contours of temperature. So we know in the tropics, QBO has a big impact on temperature anomaly. There's positive and negative anomaly sitting right underneath. The one thing I want you to look at is the negative anomaly in ACL in northern hemisphere mid latitude, both in observations and model. When there's QBO easterly, it's acting on temperature anomaly and also ACL changes. This is related to circulation changes from the tropics, moving low ACL air from the tropics to mid latitude or not. So we looked at the QBO impact on ACL, but we still don't know what happened in recent years. So we have to come up with some other explanations. What about the southern stratosphere warming? And it turns out 2019 was an extreme case southern stratosphere warming. Does it have anything to do with changes in ACL in the lower stratosphere? Okay, we can maybe further investigate. So this is a table from paper published by Lee et al. In 2023. They documented every single year it was either a strong SSW year or minor or no SSW. So remember, 2019 was very strong SSW year. Okay, let's look at then QBO easterly shear phase, maybe potentially SSW and ACL all together. So to look at the SSW impact on ACL, what I did was I picked all the QBO easterly shear DJF year and then chose when there was SSW or no SSW. That's the plot on the left. The plot on the right is the same figure, looking at the QBO impact on vacuum ACL and temperature. And I forgot to mention this purple box is the reason we have this time series of ACL, just one small reason. One thing when I look at this figure, both SSW and QBO easterly has the same sign. Changes in temperature and changes in ACL. Maybe that act favorably together. Now we're looking at changes in temperature and ACL. Did actually circulation change it in the stratosphere? For that purpose, we use something called mass stream function from Wacom 6. The mass stream function shows where the air moves, how they move. So first of all, I wanted to look at QBO impacts on circulation. So on the left is QBO easterly composite. In the middle is QBO westerly composite. In general, the positive number in mass stream function means clockwise circulation, and negative is counterclockwise. You can envision this large-scale circulation up-rolling, down-rolling in the stratosphere for winter hemisphere. So when I made the difference between these two, this is what we get from these two differences on the figure on the right. So the blue is circulation going counterclockwise. Red is circulation going clockwise. So, and trust me, okay, I added this big arrow in the middle. So circulation is coming from the tropics to middle latitude. So ACL is low in the tropics. Hey, it's moving low ACL to the latitudes. Then SSW or QBO is gonna act maybe the same way. So this is a plot that I combined, okay, changes in ACL and temperature is on the left, and changes in circulation and temperature is on the right. Low ACL is coming from tropics because of the increased transfer from the tropics to the middle latitude because of QBO easterly and SSW, maybe. That's what I think. So I'm almost done here. So remember in 2019, January 2019 was a QBO easterly shear month and with really strong SSW. The figure on the right is just 1 month. This MLS temperature anomaly, color shaded, and the solid lines are wind field. So look at the tropical area. There's easterly wind shear. Above it, there's warm temperature anomaly. Below is cold, and circulation is acting downwelling, upwelling, and then the air has to go somewhere and going to the middle latitude. This is where the low ACL is moving to the high latitude. And if you look at the literature, there are tons of literature about this QBO forest connection, especially something called Houghton-Tan effect. This came in the 1980s. So we saw after maybe 2015, there disrupted QBO, maybe this teleconnection between QBO and SSW may be acting more strongly than before. So this is my summary slide. So it's important to look at inter-annual variability and trend in ACL in the stratosphere. Wacom 6 is not perfect, but it does capture some trend in ACL. The not so perfect part is maybe related to not enough ACL is coming into the stratosphere. Maybe it's related to emission. We don't have this unreported production of CS11, for example, and we don't have very short-lived species chemistry going into Wacom 6 SD. We are going to work on this in the future. And the relationship with QBO and SSW may be acted on ACL changes in the middle latitude northern hemisphere in recent years. This is what we found. This is what I have.
Any questions?
So we certainly can run the VSL code that the people have been talking about and get an idea of how much for that chlorine for the very short-lived species is going to affect it. That'll be fun. We should do that.
Yeah, that's a good idea. Okay. Thanks. That was very.
So in your case,
When do you want to?
QBO disruption 2016, QBO disruption 2016 is much less impact than duration of stratospheric warming of 2019, correct?
Yeah. That's interesting. Yeah.
How long was SSW in 2019? How many days? Do you remember?
Okay, so next talk will be given by Ren Smith on evaluating the model representation of Asian summer monsoon UTLS transport and composition using airborne in situ observations.
Thanks. Yeah, so I'm Red Smith. I'm a project scientist in ACOM. This is work that I've presented in parts before, but since I last brought it forth in this forum, it's made some considerable changes, and we have an accepted publication as of last week, and so I'm kind of here to just give the final word on it. I can't acknowledge everybody by name because there's so many people that help with this, but just take a moment to acknowledge everybody. So what I want to do in this talk is not only talk about how the model is performing, but also just talk about a little bit about the approach that we use to actually do this evaluation in the first place. So the Asian monsoon is, I could spend the entire talk talking about how the Asian monsoon is important, but I'll just mention that it's important and that we're going to sort of break down the different processes by which boundary layer pollutants over Asia can be important for impacting stratospheric chemistry. And just really global atmospheric composition. So I'm going to use this to roadmap throughout the talk. First, we're going to look at how the models are doing with deep convective transport. We're going to look at the entry concentration of constituents into the stratosphere, so really the concentrations near the tropopause, and then also how the aging processes in the lower stratosphere look. Briefly just mentioning that we're looking at 2 different model simulations. We have a 110 level version of Wacom. We also have a 32 level version of Musica, which, as I understand, the 32 level version of CamCam is going away. But nonetheless, this is the old low top model configuration. And then the airborne observations we use are from StratoClim, which is a 2017 campaign over Southern Asia. You can see the flight tracks in black and sort of how they relate to the broader upper troposphere anticyclone that forms over Asia. And one of the things that I want to emphasize here is that throughout the talk, the comparisons that we do with the model are using this gray box that sort of loosely subsets the general region around the StratoClim campaign rather than doing a point-wise comparison. The reason we do that is because it can be challenging, as you see in the lower right, it can be challenging when you have a model grid cell that's tens to hundreds of kilometers on a side, and then you fly this comparatively tiny airplane through it that essentially is only measuring a very small fraction of what that model grid cell is. So we're looking at general representation here by the airborne observations compared to the models. So 12 minutes is short, so I'm going to just jump right into it. This is the first sort of process we're looking at is deep convective transport. We're looking at CO concentration. On the top, we are, this is an adjusted tropopause relative altitude. I should just call it tropopause relative altitude, but I've just added the mean tropopause so that the y-axis is a little bit more physical. And the bottom is just potential temperature. Slackers and Musica are shown. The mean lines are shown as, or the mean is shown as a line, and then the sort of spread between the 5th and 95th percentile there is shown as the cloud. And so what we see from this is that Wacom and Musica simulations here are really doing a good job representing the level of convective detrainment, which is a couple kilometers below the local tropopause. And then also in the lower panel, there's the shift where the CO observation, or the CO concentrations are essentially constant with altitude, and then all of a sudden they start, there's a kink, for lack of a better word, as they shift from convective dominated transport into this slower diabatic ascent. And so Wacom and Musica are doing a really good job with that. So it's a good news. I didn't promise there would only be good news in this talk. This is the same plots for ozone. You can see here that the general characteristics are represented in the model, but there is a clear high bias in the ozone concentrations. We've looked at this, a couple different sensitivity studies, looking at the impact of the VSL chemistry that's been mentioned a couple times this week, looking at tuning the lightning NOx parameterization. These can have an impact, but they're not enough of an impact to explain this. So it's still a topic of future work. Next, moving into the stratosphere entry concentration, which is a fancy way of saying tropopause. Tropopause region or layer concentration. We're looking at the same adjusted tropopause relative altitude coordinate here for various species. So there's CFC12, dibromyl methane, HCFC22, and N2O. All of these overall pass the eye test. They look, the models are doing a pretty good job here, as the eye test can say. But of course, one could accuse me of just picking panels that look really nice to present in this talk, and that would be a fair criticism. And so instead of just looking at things and saying they look good, let's actually create an error diagnostic to look at more species all at once and actually be a little bit more quantitative. So this is a pretty simple formula, and specifics don't really matter. I'll just mention that it's really the difference in the tropopause layer plus minus 1 kilometer from the local tropopause. The mean observed value there by the aircraft and the model value, and we're going to compare those and compare those against the full range of observed variability. So everything you really see from the aircraft observations. And so then if we do that, we can present this really nice table for a bunch of different halogenated species that are represented in the model. And then we can actually start to be a little bit more, quantitative with this and look for general characteristics. And so by and large, a lot of species are performing very well. You know, errors there within 10%, which we consider to be very good here. There are a few species then that pop out, so we have the ability for this to raise the alarm bells on us, I guess, a little bit. Two different places I'll highlight. First one is the methyl chloride, methyl bromide species, which I'm going to talk about next. And then there's also CFC 114 and 115, which I'm going to come back to those in the third chemistry diagnostic. So we actually, because of that realization with the methyl chloride, methyl bromide issues, we decided to do a bit of a deeper dive with these species, and we looked at these plots here, methyl chloride on the left, methyl bromide on the right, and we put these in a chemical coordinate space. And the black dots are still from our stratoclim observations, but I've added a set of gray dots, which are actually taken from the Seekers campaign, which was over the CONUS region in 2013. And what we see actually is that the Asian monsoon models are matching the North American observations, but they're not matching the Asian monsoon observations, which is what we would expect them to do. And so on the last slide, I didn't mention all of those species, with the exception of one, are simulated with are prescribed at the surface using a zonally average mole fraction boundary condition. Clearly, for a lot of longer lived tropospheric species, this doesn't matter, and that a lot of those errors looked very good for those species. But for these particular species, they're particularly short-lived compared to the others in their tropospheric lifetime. So they're not going to be as well mixed. And so with that in mind, you have this very potent regional emission source over Asia that's not being represented because that regional emission source is being smeared out on a zonal average. And so as a result, you get these models that match the Asian monsoon background, if you will, that's the observations over CONUS, and leave these Asian monsoon observations in a different world. And so this is what I basically just said, but we assert then in this work that based on this, the zonally average mole fraction boundary conditions are not appropriate for these shorter lived species. They're just fine for the longer lived CFCs, but for these shorter lived species, they're leading to underrepresentation of some of these emission sources. And I think it's also worth noting too that it's really that last slide, the diagnostic approach that we created, that really raised the alarm and allowed us to look into this, to be able to say something about this in the first place. And then this last slide here, and I wish I had subset these panels here. This is the figure from the paper, which looks very nice in a paper, but when you put it on a screen, then everything's very small. But this is, what's that?
And it's a tiny screen.
Yeah, exactly. It's a pretty small screen in the room too. It's not like the main seminar room where we're kind of spoiled. This is the lower stratosphere chemical aging. And so this is a number of species, actually, 12 of them, that are put in N2O chemical coordinate space to look at how sort of the aging processes work in the lower stratosphere. And as I've said before, for the previous two diagnostics, vacuum and music are showing similar behavior. There's compact tracer relationships. A lot of them are agreeing really well in terms of where they fall on this tracer-tracer plot. I will spare, I don't have time to go into a theoretical argument here, but we can actually look at how we can use the slope of these tracer-tracer relationships to evaluate how the model is doing in terms of its chemical aging processes in the lower stratosphere. And so we have another error diagnostic that we use essentially just to compare the slopes of the observed tracer relationships with the modeled tracer relationships, and then put them together in another one of our nice fancy tables here, and then derive some insight rather than just looking at a bunch of panels and wondering what we care about with that. So we have actually two different chemical coordinates here on this plot, N2O and CFC12, but the story is basically the same regardless of which chemical coordinate or which species you use as the chemical coordinate. But this is where I said I promised I would come back to these CFC 114 and 115. By and large, most of these species look pretty good. Again, the errors less than 10. A few of them are between 10 and 20. Overall, not too bad, but CFC 114 and 115 seem to have a clear issue, and we noticed that in the previous sort of tropopause concentration diagnostic as well. And what this then prompted us to look at then is what's wrong with these loss processes in these species. And actually, among all of these different species, I've marked with a little asterisk, but I'll make it a little bit more clear with these arrows. All of these species here have loss processes in the lower stratosphere that are dominated by photolysis. And all of those species, by and large, have pretty good agreements, but the ones that don't, the ones that have OH and O singlet D as important loss processes in the stratosphere, these are the ones that show a little bit more of an issue. And so we're actually wondering when they are ozone bias that we went back all the way to the beginning of the talk, if the ozone bias is having or playing a part in these species not being having concentrations that are properly represented. Okay, so I'll summarize here really quick. We use tropopause relative altitude coordinate, a stratosphere entry diagnostic, as well as using a long-lived tracer as a chemical coordinate, showing that Wacom and Musica overall are doing a pretty good job conceptually compared to the observations. They're agreeing pretty well with the observations. We saw that the zonally average boundary condition might obscure important regional emission sources for those shorter-lived tropospheric species. And I think I'll reemphasize something that I mentioned right at the top, but again, these process-based diagnostics that we have here are really trying to minimize the fundamental air mass size disparity between these comparatively large model grid points and comparatively small in situ observations. So we hope this can be a useful tool for us in the future. I'd be remiss to not point out that we'd like to apply this to the ACLIP 2022. Stratoclim feels like a bit of old news at this time, but we knew that if we injected this new campaign, we probably never would have finished the paper. So we just stuck with that, and this continues to be future work. There's also some push now for development of this CAM-MPAS with chemistry, which is being worked on at ACOM a bit. And this is something that can explicitly resolve convection in a global grid with chemistry. And so this is something that we might want to include. This might actually go with the ACLIP observations or with the ACLIP analysis that we want to do eventually. And lastly, it would be nice to use this same diagnostic framework to explicitly talk about looking at the role of horizontal and vertical resolution, or the impact that horizontal and vertical resolution can have. Originally, when we did this, we wanted to do that, but the Wacom and Musica simulations we use are just have some subtle enough differences that if you see differences, we wanted to say, oh, look what the horizontal resolution is doing for us. But if they're not otherwise identical, this is something that we can look at in the future. So, sorry, thank you.
Any questions?
Yeah. Okay, so let's pick on CFC 115. That has a relatively long stratospheric lifetime, about 500 years.
Mm-hmm.
So I'm not sure that in the lower stratosphere, that's where the problem is, right? It's going to be up in the upper stratosphere where it's destroyed and transported to that region.
Interesting. So it might be a different process.
It might be a different process, yeah. There was an update to the O singlet D plus CFC 115 rate constant at one point. I think we have that in our model, but I should double check that.
Okay.
So it almost looks like they are opposite. Is there something that maybe some of the CFC 14 and 15 got mixed up in something in the boundary conditions or something? Because it almost looks, if you put them together as one, they probably fit nicely. If you just do 14 and 15.
Yeah, and that's the slide here, seeing the slope is the loss rate is too fast in one and too slow in the other.
Right.
And I just brought this slide back. The very lowest right panel there is the CFC 115 versus N20, and this one is the most egregiously wrong looking panel out of the 12. I can't comment on the sort of upper stratosphere, but that's a good point that we wouldn't necessarily expect it to be destroyed that quickly leading up to the lower stratosphere, especially due to the Asian monsoon where you've got commonly upward motion.
I don't know, we can offline, let's take another look at it all.
Definitely.
Just one quick interesting comment is that we do have the very different models. The Musica highly refined, and then the Wacom that has much better vertical resolution, but still they perform fairly similar.
Yes.
And that shows somewhat that there are other things that you can detect that may be actually influencing. So high resolution doesn't necessarily give you a better answer of the problem. in this case at least. So, yeah, it's interesting to see.
Yeah, I de-emphasized those. I had to, part of the first submission and then the second submission after revision, I had to de-emphasize all of those details, but I think it's,
yeah.
And so I did the same thing here, but it is something that will be worth looking into more, I think. But interesting that, like you said, that there's not a lot of significant differences.
Yeah, thank you again.
Yeah.
So we'll move on.
Do we have online?
Yeah, so next talk will be given by Susan Nossel. Susan, I have your slides. Do you want me to share them or do you want to share?
An actual situation.
Sure, that you can share. Thank you.
Okay.
Or-
Okay.
What's why you break out December, January, February?
I'm not sure I will not.
So it's very long.
Can you share?
Otherwise, I
Yeah.
can share too. I have them here too. So whichever is better for you.
They let you take over screen sharing.
Oh, thank you. And I think also during the talk I'll turn off my video just because I'm looking at some notes, and then I'll bring my video back on for the afterwards for any questions. And thank you so much to the organizers and the many people who have contributed to the work that I'll present today, both the modeling and the observational aspects. And again, thank you to the organizers of this workshop, and I've learned so much. So thank you to the other presenters too. Okay, so today what I'll be doing is I'll be talking about climate studies with Wacom-X and discussing the whole atmosphere simulations of the thermospheric hydrogen response to increases in greenhouse gases and to changes in solar activity. And the changes in solar activity are a major source of natural variability in the Earth's upper atmosphere. And then we very much appreciate any feedback, suggestions, and possible collaborations, especially with people studying hydrogen-containing constituents at different altitudes. Next slide, please. So thermospheric hydrogen is a byproduct of hydrogen-containing species below, such as methane and water vapor. And methane can transit the cold tropopause, and so it's a major source of hydrogen-containing constituents in the middle and upper atmosphere. And chemistry and photolysis reactions convert methane into water vapor. I think formaldehyde is part of that process. Eventually, atomic hydrogen is produced in the thermosphere and exosphere. And then given the kilometers-long mean free path and orbital trajectories of the hydrogen atoms up in the upper thermosphere and into the exosphere, the distribution of upper atmospheric atomic hydrogen may be more uniform compared with the distributions of hydrogen-containing constituents at lower altitudes. So one of the goals of this work is to contribute toward whole atmosphere pattern studies of hydrogen-containing species across atmospheric regions, and to understand and to the understanding of possible vertical footprints of climate change processes. And other studies of other parameters are indicating that vertical patterns of changes across atmospheric regions can provide insights into natural variability and climate change processes, as well as additional information for attribution. Next slide, please. So on the left side are two figures that are from the seminal studies published in 2018 and 2019 by Stan Solomon et al., who used Wacom-X with perpetual solar conditions to simulate the temperature response to increases in greenhouse gases from the warming at the surface through the cooling of the upper thermosphere with a single self-consistent model. The physical mechanisms differ with altitude, but this model, to me, it seems it's such an amazing accomplishment of this, Wacom-X team, the whole CESM team. I come from an observational background, so I just wanted to share. I just think this is an amazing, accomplishment for all of you. yes, so this model is able to simulate both the warming in the lower atmosphere and the cooling of larger magnitude in the upper atmosphere. So today, what I'll be presenting is that we analyzed these Wacom-X simulation results, but for the hydrogen in the upper atmosphere, to investigate magnitudes and processes relating to the hydrogen response to the greenhouse gases and the solar cycle. And then we're using, as I'll show later, we use forward modeling to compare these results to ground-based Fabry-Pro observations of thermospheric and exospheric hydrogen Balmer alpha emissions. Those are air glow emissions. So in the two figures to the right, the blue curves are 5 ensemble runs from Wacom-X from the early 1970s, and the red curves are 5 ensemble runs from the early 2000s. The right figure is for perpetual solar minimum conditions, and the left for solar maximum conditions. And unlike the total thermospheric neutral density, which decreases along with atmospheric contraction due to carbon dioxide cooling, these numerical simulations indicate that the atomic hydrogen in the thermosphere is actually predicted to increase with rising concentrations of greenhouse gases. And the mechanisms could be that methane increases the source species for hydrogen, and that cooling by carbon dioxide also contributes to the increase in simulated upper thermospheric hydrogen density. Something else that we can see here is that, oops, oh my, sorry. I just realized something that was wrong here, very wrong. This, the left side should be solar, sorry, the right side is solar maximum and the left side is solar minimum. That's I'll send you revised slides. I'm sorry, something happened here, but the right side is solar max and the left side is solar minimum. So right side is solar max, left side is solar minimum. So what we can see here is that so these captions at the bottom are reversed. So, but what we can see is for the left side plot, which is solar minimum, that the hydrogen densities are higher than for solar maximum. In both cases, there's an increase in density with increases in greenhouse gases, and furthermore, the increase in the response of the atmosphere of hydrogen to greenhouse gases is dependent on the underlying solar conditions, solar activity conditions. So for solar minimum, again, the left side plot, there's a larger response than for the right side plot and at solar maximum. And this is consistent with a larger magnitude cooling in the upper thermosphere for solar minimum or low solar activity conditions. And those are displayed in the plots to the left from the Solomon et al. Papers. Okay, next slide, please. So here we are using forward modeling to compare the Wacom-X simulations with observations. So what we do is we input the thermospheric hydrogen and background conditions from Wacom-X to calculate the thermospheric and exospheric hydrogen Balmer alpha column emission intensity, which is an air glow intensity that would be observed from a ground-based Fabry-Pro instrument. And this is a solar excited emission, and so we plot these intensities versus the altitude of the Earth's shadow, because most of the emissions are coming from above the Earth's shadow. And what we see here is the left side are observations where the red are during solar max and the blue, orange are low solar activity, so higher intensities at solar maximum. Likewise, the triangles are higher intensities during calculated intensities during solar maximum than during solar minimum. So there is qualitative, the sorry, that there's qualitative agreement between the solar max and min comparisons between the observations and the calculated emissions from forward modeling. These column emission intensities depend on both the hydrogen density profile and also the solar Lyman beta flux, which excites the hydrogen atoms. So the line center solar excitation flux is also a source of uncertainty in the forward modeling. Next slide, please. So these are profiles from the WACMX upper thermospheric hydrogen density and background thermosphere, and that are used in the forward modeling. And these are for solar max and solar min for one particular year. And it helps with, it demonstrates, it provides information about the solar cycle comparison. What we can see here is that during low solar activity, WACMX upper thermospheric hydrogen density increases while other background species decrease. And this is, again, solar cycle. And Liang Chen, in a 2018 paper, discuss how complex dynamics, including diffusion, likely contribute to hydrogen variability with solar activity. And it may be that a similar process is happening for the carbon dioxide cooling, and how the carbon dioxide cooling may be impacting hydrogen due to greenhouse gases. We see increases in hydrogen in multiple types of modeling and observational studies over different time scales that correlate with cooler temperatures, such as dawn-dusk asymmetry over between two different twilights, or the solar cycle, and also the greenhouse gas that we just mentioned. Next slide, please. So this is a merged, this next figure shows the Northern Hemisphere merged mid-latitude Balmer alpha emission data set. All of the observations were taken with ground-based Fabry-Pro spectrometers. The observations to the right of the rightmost line were taken with the Wisconsin H-alpha mapper, or WAM instrument, when it was at the Kitt Peak Observatory in Arizona. It's now in Chile. And the earlier observations were taken from Wisconsin. Ed Merkowitz has recently moved Fabry-Pro back to Wisconsin, and we'll be starting to take observations again from Wisconsin. And because all of the observations are calibrated with astronomical nebular sources, that will help us to merge in new observations to this data set. So each of these points is a bin representing spanning winter conditions and represent at a mid-range shadow altitude and representing many spectra. But the data, if we look at 1990, 91, and then the 2000, 2001, these are two solar max or near solar max data points, and the data suggests a likely increase in hydrogen emission intensity between two solar maxima, with the caveat that this is a limited data set. Next slide, please. So this is the forward modeling, again, with WACMX simulations. The plot to the right are the solar maximum, solar maximum, the perpetual solar maximum runs, where we are comparing the 1970s with the 2000s, blue 1970s, 2000s in red. The plot to the left are observations where the 1990-91 observations in the greenish colors are same observations but plotted with different calibration sources, giving an estimate of the uncertainties in absolute calibration. And then the blue-red are the later years. What we can see here is that the forward modeling likely does not account fully for the apparent increase in the observed hydrogen emission. The forward modeling is over 30 years, the observations over 10. Next slide, please. This is Hanley, I think on Monday, mentioned the long climate runs with WACOMX, and this is one very recently published by Joe McInerney. And this is this is the past century hydrogen past century runs. And this particular plot talks about the hydrogen and the neutral density. As we can see, the neutral mass density. Oh, let me also say that these runs are again time slices. It's for perpetual solar minimum conditions, but the time slices are every 10 years now. And as we can see here, the neutral mass density, that's the top left plot, the neutral mass density decreases as the carbon dioxide is rising. So the atmosphere is contracting, and then in the upper thermosphere, the total neutral mass density is decreasing. In contrast, the atomic hydrogen is increasing over this period of time, and its shape is somewhat correlated with the shape of the methane increases. The plots to the right foremost plots are the percent difference in the altitude profiles. And what we can see here is that the biggest change in the neutral mass density occurs in the most recent years, where there is the steepest rise in carbon dioxide increases. And then for methane, the largest rise in the methane over this particular period of time was in the middle part, and that correlates with the largest change in hydrogen, atomic hydrogen. Methane is unfortunately again increasing more recently. Okay, next slide, please.
Just so you know, Susan, it's been 15 minutes, so if you could wrap up soon, that'd be great. Thanks.
Oh, I'm so sorry. The next one is a conclusion. Okay. Okay. Well, just said that the upper thermospheric hydrogen is increasing due to greenhouse gases, or simulated increase due to greenhouse gases. There's some I'll just say that it depends on solar activity too, and there's areas of agreement and disagreement with observations. And next slide, please. Okay, and then ongoing and future work, adding new observations, and then using modeling comparisons that more closely align with the time frame and viewing geometry of the observations. And next slide, please. And then these are a couple questions that we have, which I'll let folks read. But one of the goals of this work is really to be able to contribute toward whole atmosphere pattern studies of the hydrogen-containing species across atmospheric regions, and we really would welcome collaborations with people studying methane and other hydrogen-containing constituents at different altitudes, and we really welcome your feedback. So thank you so much.
Any questions for Susan?
So Susan, thanks for the great talk. I was wondering for the hydrogen long-term observation, it seems that you were presenting results from mainly from Wisconsin, right? Or solar cycle, maybe I got mixed up. The long-term measurement of upper atmosphere hydrogen.
Yeah, they're mid-latitude. They're hydrogen from Wisconsin and Kitt Peak, Arizona.
Kitt Peak.
Both of them. But some are aligned together. But I mean, there is some overlap, but there are also some that are from different locations at different years. Yeah.
Are there any like after the moon landing? Are there any long-term measurement from the moon of the geocorona, or any way to infer those kind of information?
Oh, let me see.
From the 60s.
Oh, I don't know the answer to your. Thank you for the question. I don't think I'd have to think about your question. These observations were only started in the early 70s. They were actually made for astronomical purposes, but then there was a terrestrial line within those astronomical spectra. And I think that when we look back at the earlier measurements, that the uncertainties were larger. And so these ground-based Fabry Pro observations, I think in terms of like the detection and the quality of the optics, I don't think the ground-based were available before the 70s, but they're the satellite observations. Thanks for the question. I would need time to look into it. So,
Thanks.
yeah, thank you.
No
Wanna
other
come up
question. So thank you again, Susan. So we move on to the last, or no, not last talk, second to last talk, which is Haipeng Lin on global comparison of tropospheric oxidant chemistry in a common Earth system model environment using geochem and chem chemistry within CSM2.
Yeah. Full screen. Yeah, slideshow. Oh, I don't know which one.
Is it sharing now?
Yeah.
It's not showing.
Because Susan, oh yeah, maybe somebody stopped sharing there.
Thank you. Good morning. Good morning, everyone. I bring greetings from the Cesm community. I'm Haipeng Lin from Harvard. I work with Daniel Jacob and many collaborators on a very big software engineering and also science project on coupling the Cesm chemical transport model into CSM2 to provide an alternative chemistry option to ChemChem's chemistry. So Cesm is kind of best known as a chemical transport model, which uses archived met fields from GS5 or MERIT2. It has a very different development heritage from ChemChem, and recent efforts have kind of restructured Cesm to allow implementation of its chemical processes into external models such as CSM2 in order to provide an alternative chemistry representation to the resident chemistry option, ChemChem. So in the past few years, we also did work on implementing the online emissions component from Cesm HEMCO into CSM2, which can provide both emissions to both ChemChem and Cesm chemistry within CSM2. And so the advantage of having these two chemical representations in under one model is that we can perform process-based model intercomparisons, whereas before when we compare two different atmospheric chemistry models, we have important first-order differences like in meteorology or emissions that are hard to disentangle, so you don't know what exactly each model has in terms of its strength and comparison to observations and also comparison to each other. And so the focus of today's talk is mostly on tropospheric oxidant chemistry. So we know that ozone is a very important species and important measure of model skill, but current models actually have a very hard time agreeing on everything, anything really. So in terms of individual processes and budgets, so they have a very large spread amongst models in terms of chemical production, loss, stratospheric influx, or deposition. And having different processes magnitudes means that there are fundamental differences in how underlying processes are modeled, which means that there are different sensitivity to perturbations, which pose difficulty for chemistry climate models that aim to kind of quantify chemical feedbacks to climate change. So in our work, we kind of look at Cesm and ChemChem representations within the CSM2 model. So they use the same meteorology simulated from CSM. It's a development tag because we're still working on the development code. It's nudged to MERIT2 using the FC nudge comset at 1 degree resolution, and we use the same emissions from HEMCO, the SETS version 2 and course version 5 anthropogenic emission inventories. And in terms of differences in two models, they're very different. The chemistry mechanism in Cesm is generally more complex. It has a full representation of tropospheric halogen chemistry. It includes recent updates are photolysis of aerosol nitrate into HONO and NO2 to correct an underestimate of NOx over the remote ocean. And also cloud uptake of N5, whereas other models generally include aerosol uptake only.
And in terms of aerosol composition, so CamCam has modal aerosols provided by MAM, but JustCam in its offline configuration has bulk aerosols, and the chemistry is by default only aware of bulk aerosols. So we use bulk aerosols coupled to MAM by mapping the bulk masses, the changes in bulk masses to the modes. And so this has a big caveat on how it impacts aerosol radiation and aerosol cloud interactions, because the size distribution can be very different from what's simulated by CamCam. In terms of the photolysis scheme, JustCam uses the FastJX photolysis, considering aerosol effects of aerosol extinction, and CamCam, in this version, we use the TUV lookup table. That's the default. So in terms of budget terms with both models, both models have very similar global burden when we look at tropospheric ozone and OH, but that's actually where the similarities end. In terms of individual budget terms, JustCam has a much hotter chemistry because it's due to in the oxygen chemical production. This is mainly driven by photolysis of aerosol nitrate, which has a lot of NOx over the remote ocean, and also tropospheric halogen chemistry. In terms of dry deposition, we have a hybrid approach where we use dry deposition velocities over the ocean from JustCam, and those over land, we use the same as CamCam using the flux from CLM. So this leads to about a 20-day difference in terms of ozone deposition lifetime. This is due to updates to JustCam's dry deposition velocities over the ocean, which are slower. And when we look at surface maps, we see that despite having global burdens, the main takeaway is that there are very large regional differences between the two models. If you look at surface OH, this is the 2016 annual mean, we see that JustCam has lower OH over polluted regions. This is due to lower geosinglet D from FastJX compared to TUV. And also because of the more complex VOC oxidation in JustCam, there's higher OH reactivity over the polluted regions, which leads to a lower OH. We see these hotspots in terms of delta OH over the Amazon Congo basins. This is due to JustCam not titrating OH in low NOx environments due to an updated isoprene oxidation mechanism in Basin JCOP 2019. So TS1 mechanism doesn't represent this, but TS2 has similar recycling, and so we wouldn't see differences in OH here if we switch to CamCam TS2. And so these differences in OH lead to kind of lower CO in CamCam compared to JustCam, because JustCam has lower CO, lower OH in general over the Northern Hemisphere, and subsequently higher CO and better agreement with the observations. If we look at ozone, we also see this compensating effects. JustCam has generally lower ozone in the Northern Hemisphere. This is due to loss of tropospheric halogen chemistry, and at the higher latitudes due to cloud uptake of N2O5, which removes NOx and subsequently affects ozone. Over the ocean, over the Southern Hemisphere, kind of effects due to a slower dry deposition velocity over the ocean kind of starts taking over. And we see that despite having a similar global budgets, there's compensating effects between the Northern and Southern Hemisphere, between polluted and remote regions. So photolysis rates are also a kind of a big driver in differences between the two models. Here we show tropospheric vertical profiles of JNO2 and geosinglet D as derived from actinic flux measurements in Course AQ and the ATOM1 campaigns. We ran the model over 2016, so we're using these two. And we see that JustCam in blue and CamCam TUV in green. The two models agree within about 5% for JNO2, but in geosinglet D, we see this very big difference, about 30% overestimate in geosinglet D from CamCam TUV that is not reproduced by JustCam, and JustCam is closer to the observations. So one would think, oh, this is in a polluted region, it doesn't show up as much in ATOM. It could be the effects of aerosol extinction, but even if we prescribe zero AOD or clear sky prescribing zero cloud optical, that the difference still persists. There's still a 20-30% difference between the geosinglet D values. And it's not the overhead ozone column, because CamCam actually has higher overhead ozone, and the difference only disappears when we use CamCam fields to drive FastJX. So we made a preliminary implementation of FastJX into CamCam, and that's when we can only bring geosinglet D down. And so it's still unknown why this difference is only noticeable over polluted regions and not as much over ATOM. And future versions of with UVX or Cloud.j, just comes update to FastJX, we'll hopefully be able to disentangle these differences. And kind of the strength of our intercomparison framework is that we can attribute particular features of models against models and models against observations to specific features in the model. So here we show tropospheric vertical profiles of ozone, NO, nitrate aerosol, and PAN over the course AQ, over the Seoul metropolitan area over the course AQ period. And you see that CAM here showing green generally simulates ozone well, but JustCam showing blue is only able to do so with photolysis of aerosol nitrate, which compensates for NOx. And the version of JustCam CESM without aerosol nitrate photolysis is shown here in the dashed blue line. But it's kind of, because we are fertilizing aerosol nitrate, this would be very sensitive to how much nitrate we are simulating. And JustCam within CSM kind of has difficulty in accurately simulating nitrate aerosol vertical profiles. Because JustCam aerosols such as nitrate and also its gas-phase precursors are not scavenged in convective updrafts. So this leads to kind of an accumulation of nitrate and also its precursors in the upper troposphere. And we can only apply correction to this to kind of bring the nitrate aerosol down, because otherwise the ozone and NO start to get overestimated by a lot. But this still doesn't get close to how JustCam offline, here showing red, which correctly scavenges in convective updrafts or observations. We still have some distance to that. And when we look at kind of PAN and nitrate aerosol below the 2 kilometers, we see that there's some vertical structure that can be simulated by the JustCam offline model, which is also present in the observations, but not present in CESM. The higher concentrations over the surface for nitrate aerosol and also PAN compared to the observation. So potentially there's insufficient boundary layer mixing in CSM compared to JustCam offline. And yes, I believe the take-home messages here, we kept seeing that JustCam can also provide a high-quality alternative chemistry option to CamCam in CSM2. It also enables side-by-side comparisons with CamCam. Our implementation of FastJX within CamCam and future efforts to put in Cloud.j will also serve as useful contributions to Musica. And JustCam also works well with the SE grid. So here it doesn't move, but we were able to run JustCam on the Korea grid in the Musica configuration. And there are important regional differences between the two models, so it could be interesting to explore. And thanks to the work of many software engineers and scientists, we were able to merge JustCam and CSM2 into a development tag of CAM 63147. And HEMCO emissions for CamCam are also available in beta versions of CESM, which provide emissions, online emissions to both JustCam and CamCam chemistry within CESM. And yes, I'm happy to take any questions. Thank you.
Yeah, so for the one case where you showed the O singlet D was, yeah, the top one up there. Do you have clouds in your model in this one?
Yes.
Okay, so it could be that we're not representing clouds as well in CamCam. And so that looks like it's offset from the very top all the way down to the bottom. That's my guess is what's going on there. I don't think it, unless we compared clear cloud J's, that would be a useful comparison too.
We compared clear sky for both cloud, for both FastJX and QE, and still like a 20% offset. The two models can just offset, but the differences are not eliminated. So maybe there's different treatments of.
We have high resolution in the ozone O singlet D cross sections in that region. I don't know what they do in FastJ. Yeah.
Thank you. I saw a question online.
Oh, there is.
Yeah.
Also?
Hi.
Hi. Very nice talk.
You can see
I
him there.
wanted to ask you about HEMCO. So you set up both simulations that with CamCam and with JustCam with the same emissions, but I can imagine that HEMCO, I never use it, that you can decide which type of emissions to use. So for this study, I mean, mostly for comparing with observations, those emissions were more similar to what Geochem usually has, or to what CAMCAMs usually have, or they are quite the same?
Thanks for your question. So these emissions are more similar to what Cesm usually has. I imagine the same inventories would be available from CAMCAM, but these would not be the default inventories used in CAMCAM. So the SEDS global inventory, and then we overlay the course emission inventory over East Asia. So I imagine it can be different from the default in CAMCAM. And there's a lot of caveats in how other emissions are handled in terms of biomass burning. We use GFAD instead of what's default in CAMCAM.
Okay.
There can be lots of differences to an out-of-the-box CAMCAM simulation.
Okay, thank you.
Thank you.
I can talk to you later, so okay. Thank you. We want to move on to the next talk, Sean?
Yeah, I don't know who is presenting. Sean, you'll present?
Yeah.
So last talk of the session, we do have some sort of formal discussion at the end, so please stay for that. Is on the Wacom and chemistry ADF diagnostics. Your slides.
You want to use it? Okay, so your talk should. So let's see.
So I'm just gonna overview the updates and progress, and overview the working group diagnostics framework, or the ADF. And this is sort of a co-presentation. Justin Richling is giving an update presentation in the other seminar. This one overviews, but also gives a little bit more emphasis on where we're going with the chemistry diagnostics. And so just to, not everybody may be familiar with what the ADF is, but what it basically is it's meant to generate a standard set of climatological visualizations between the CSM simulation that you run and compare it with either another CSM simulation or observations or analysis data sets. And the diagnostics of itself has been around for a while, but we've kind of swapped over to from NCL-based code to Python-based code. And this has been, I think, largely done by Justin. And so there's a lot of stuff available out of the box. It's all open source, and you can even produce your own custom diagnostics if you want, and potentially even contribute your own code if you want it to be available to everybody else. And it's meant to run primarily on the NCAR. It's built to run on the NCAR Casper computer out of the box, but with the proper Python modules, you could run it on any computer, really. And so to get a hold of the code, it's all available on GitHub. NCAR's GitHub page /ADF. And it's pretty easy to use. You just get it off of GitHub and activate the Python library on Casper NPL, and then configure. There's a configuration file in the parent directory of the software. You configure it to the way you want to, how you want it to run. There's even an example one in there that you could just literally run it just to see how it works, and then you configure it as to whether or not you want to compare it with another model output, or if you want to compare it to data. You specify what variables you want to plot and visualize, and you can even put your own custom plotting scripts in there, and then you run it, and it should generally work. And out of the box, what you'll get is you get netcdf outputs of time series files, climatology files, and netcdfs regridded onto pressure levels. And there's a whole suite of plots that you'll get, and some data tables, and then you get a nice HTML file that neatly organizes all that so that you can view everything. And I'll just kind of show what some of these out-of-the-box plots look like. Here, these are just some global and polar plots. Generally, how these look is you'll get whatever your simulation that you're looking at is, along with a comparison with either another simulation or in some cases observations, and then you will also get a third one with plot on there, which is a difference plot. And you get these at various, I think, pressure levels. And there's also zonal mean plots and Taylor diagrams. On the left, there's the zonal mean plot, the Taylor diagram on the right. And I believe that this will, when you add, there's a standard set of variables that it'll put on the Taylor diagram. I think if you add variables, I think it includes those as well.
Some of them, yeah.
Some of them. Yeah. These are just examples of wind vector plots. This is a surface wind vector plot with a similar 3-panel format. There's also QBO plots. I think this is technically this is the one that's in there right now. I know Justin's working on a new one, I think. And this is also a 3-panel plot, although it's comparing with this one's comparing with the model output. And this is just an example of the HTML that it outputs. And so everything's kind of neatly organized in there so that you can view all the outputs, and you can just basically double click this file and it'll open it in a browser, or if you put it on a host server, it works the same way. And everything's just neatly organized so that you can go through and diagnose your simulations. And I mentioned that you can create and contribute your own diagnostics. There's kind of a whole section on the GitHub ADF site for contributing your code. There's a wiki there, and there's a sublink for the contributor's guide. But generally speaking, all you really do is you take a piece of code that plots something or generates something, and you throw it in a particular folder subdirectory in the software package, and generally speaking, the ADF can locate that and include it in the diagnostics output. And an easy way to kind of get started doing that, there's, for example, the plotting directory, subdirectory, there's a bunch of examples in there that you can borrow from to kind of build your own. And then if it's something that you want others to be able to use, you could literally take that and push it back to GitHub, and Justin may make a few changes to it, but if it's something deemed useful, it could end up in a future release. So that was kind of just a general overview of the ADF itself. and so the newer diagnostics package is still a work in progress. And Justin's working on a lot of this, but we're helping get in some of the chemistry diagnostics, which is largely still missing. And so basically what we're helping doing is porting some of the previous diagnostics over to this new version. There's some stuff that is already there, the map plots, global and polar, some of the data table information is there. In some regards, the Taylor diagrams and zonal mean plots and time series. There's a fair amount of stuff still not included yet. There's, comparisons with some of the satellite data, comparisons with aircraft, some of the seasonal cycle stuff isn't in there. Ozone climatology is not really in there yet. And then, any of the new and updated diagnostics later on. But I just kind of highlighted the ozone climatology. That's one of the first things that I've been helping with to try and get in there. So I was just kind of showing what that looks like. And this is just an example of the seasonal cycle plots. On the left is kind of the older NCL-based version. On the right is where I'm at with the new Python-based version. And this is the ozone profiles, and so same sort of deal. The NCL version on the left, the Python version on the right. And for these are compared with ozone son climatology, and this will hopefully be getting added in pretty soon as a standard option for the ADF. And this was I know some stuff that I think Justin is working on right now. I don't know exactly when this will become standard, but because it's all work in progress right now. But I know he was, from some email exchange just over the last day or two, some new stuff that is going in. On the left is polar temperature plots, and a different version of the QBO plots on the right. So hopefully that'll be also coming in relatively soon as an update to the ADF. And so for the chemistry specific stuff, we maintain a page on our ChemChem wiki that covers what we're working on, or what's being worked on with the ADF, and kind of what our wish list is, and if there's any active issues published to the ADF GitHub, they're on there. And so if anybody wants to keep up with that, it's on the ChemChem wiki, which is wiki.ucar.edu/display/ChemChem, and there's a link under there for the ADF. And so, and on the right there, I just have this is kind of our current wish list. A lot of these things are being actively worked on and or will be gotten to hopefully relatively soon. So with that, I will take any questions. Assuming I'm doing so on time.
Any questions?
So maybe a comment to add, everybody that wants any diagnostics in there. I mean, it's something we need to work together on, because there are so many things that we may want to add. It doesn't have to be specifically to chem or ChemChem. It can be diagnostics, can be also what ChemX, for example. Because you can design your own diagnostics in Python based, and it's actually quite easy to add things. And it's just something that we have nothing anymore to compare our model to since the AMWG NCL diagnostics. I don't think they run anymore. So kind of now trying to really merge things over. So input is really helpful if people have input, what is useful. And I mean, Rebecca, you may talk a little bit on the melodies diagnostics. I don't know.
I wasn't planning to.
So
talk
we
on
do,
that,
yeah, we do have also another diagnostic set that is really based more on aircraft campaign, focus on air quality.
And surface.
This is really focusing more on the climate, more the climate type of simulations, the 10-year comparison, but also the seasonal cycle. And so there's many things that, yeah, that people hopefully contribute and in the future. You just have to start, and once you start, it's actually not that hard.
Yeah, but it's all kind of meant to be, Justin kind of set it up to be sort of plug and play a little bit, so you can plug in your own sort of diagnostics, and it's meant to be done relatively easy so that
Just to change the online. But one last thing to add is the good thing is Sean has actually now looked into it and he can help us. So
Yeah.
if you do have something that you have as maybe NCL code even, but you can make it in the Python code or not that we promise too much, but at least we have somebody that can help and is accessible to move forward with diagnostics that Justin is doing a lot, but he cannot do all the time everything for us, for our group. So that's what we're trying to do. Yeah.
I have a question, Sean. So if say we have a WAC-MX output and we let the package read it, does it automatically adjust to the vertical level when you do a zonal mean plot? Will it do that, or it will just you have to somehow dig in the code a little bit?
So I think right now Justin's zonal mean plots only go to a specific range, but it's not hard to change it.
Okay.
In fact, I'm trying to remember if, actually, I take that back. I think he's got it worked into the configuration file now where you can actually specify partial levels, I think.
Oh.
So you can specify the range, I believe.
So he already has two zonal mean plot types. One is a, more like tropospheric focused one, and one is a low pressure type.
That's right. Yeah.
And if you can change the range, then that will be perfect. And actually, you just need to add, like, in this YAML file that you use to control it, if you right now add any chemistry, it produces those files already for you. Because you can just tell it what to do, and then it may not look, I don't know, it may not look like you want, but Python automatically chooses some color ranges, right? So it's at least worth throwing it in and having a first look.
Yeah.
And that can be just for yourself, but if you can make your own configuration for WAC-MX even, if you wanted to, and that is more, friendly for the other users too, to use it that way.
Yeah.
Yeah, we don't. I have not used it. I was
okay.
thinking we should look because we don't have anything for WAC-MX other than
Apart from the IDLGOV. We use the IDLGOV.
Right, and it is nice, but this is nice when you just get the zonal plots
Yeah.
thrown out, and it does do all the averaging for you if you have 10 years or something like that.
Right.
The package.
Yeah, I just wanted to mention Jesse is here too, and
Yeah.
Jesse works a lot with the ADF as well. Justin's been helping us with the chemistry very much, but yeah.
Are you developing the ADF as well?
Yeah, I'm like the software engineer tasked with the ADF. Although I've been pulling off, Justin's been definitely picking up more of the slack than I have, but yeah, I was willing to hear to make sure if there was questions, but yeah, it sounds like Sean, everything that's covered. So.
But it's good that you guys, Jesse too, for questions
sure.
and exchange, because our question, I guess, is also how fast it gets into the versions that people can use it, because I think Justin always said there has to wait for approval. And that seems to be a little bit of the lack of time.
That's me. So,
Hi.
That's the problem. Is there somehow we can help to make that, or is there something you have to go through all the code and have to actually review it?
I don't have to. We do have someone should go through all the code just because it's good practice to have someone else look at the code. But
I think we help maybe by just writing good code.
Sure. Well, I mean, you can always request Justin, Yeah, I mean, the idea is, Sean or who would open a PR, and then Justin or I or someone else would just look through it. And we're not necessarily looking to see your science is correct. We're just looking to see like, oh, do you have any obvious bug in here, or do you, is there something that, you're looping twice and you can loop once or something, just things like that. So yeah,
It's good. Thanks for coming, because now you know who's maybe putting some pull requests into the.
Well, it's cool that you're adding, because Justin will tell me there's chemistry coming, which was pretty vague. So yeah, it's nice to see. Yeah, what's actually going to be this? Cool, thanks.
Thanks. Okay, should we move on to the discussion? People may be starving already.
Well, we're supposed to. It says we're supposed to end at 12:30. So.
Well, we can do a little discussion. You prepared some slides. If people are interested in that, I think there are some things that may be useful, just at least the beginning. If you guys are hungry and want to leave, that's fine.
We can quickly go through it.
But we don't have to go through everything, but yeah, if you sharing.
So we're supposed to be in the wrap-up discussion session now. That was planned after Sean's talk. And I just had a couple of slides at the beginning that I wanted to make sure everybody was aware of some resources we have. And then there were some discussion points that maybe we want to talk about. So I'm sharing the community liaison role with Sean for the Chemistry Climate Working Group. And Midong is the community liaison for the Whole Atmosphere Working Group. And so the first resource I wanted to make sure everybody knew about was this chemistry modeling wiki. We started it out as just a CamCam wiki, but really there's a lot of information there that's useful for Wacom as well. So we changed the name to the chemistry modeling wiki, but the web address still has CamCam in its name. But so that's really useful. It's got things about data sets that go into the model, how to run the model on the HPC, etc. And there's a link there. The other thing that's important on the wiki is a user details section. And so right at the top of that page is a link to a Google form where you can update details about what you're working on with the chemistry modeling. So the wiki was the first thing I wanted to talk about. The second is for the Chemistry Climate Working Group and the Whole Atmosphere Working Group, we have parallel web pages that are kind of outward facing to the community. We're working on updating these. They're more stable web pages that just have information for the community, like publication lists and what we work on, development updates. But just to make you aware that we have those. If you see anything that needs updating on those, feel free to let any of us know what needs updating. And then we have this discussion board forum section where people can ask questions about issues they might be having with the model simulations, and there might already be answers to their questions. And there's a forum for CamCam and a forum for Wacom. And so I think some of you are already aware of these forums because I've asked you to help answer questions, and I will continue to ask for help. Thank you very much to those who have helped answer questions. There can be a lot of questions on there. One important thing that maybe I want to make you aware of as question answerers as well as askers is when you go to ask a question, there's actually instructions on what you should put into a discussion board post. So there's this link at the top of this when you open up Ask a Question, and it has a whole bunch of information on instructions on what to include in a help request, things like the version of Cesm you're using, etc., etc. So just to be aware of that, and if you're answering a question and just says, I can't get the model to run, maybe then point them towards, here are the instructions on what you need to say before we can help you with your question. Then finally, just quickly, we had this big move to derecho the new HPC, and a lot of input has moved from because Glade P was removed. So that was where a lot of the input for the model was stored. It's now in a holding place on Campaign Store. So a lot of, for example, the fire emissions are in a holding place on Campaign Store under ACOM Weather or ACOM Climate. At the end of February, that's all going to be moved to like a ACOM Musica input area. So just some information there. There's a link to a spreadsheet that shows where it used to be, where it is now, and where we hope to put it.
Yeah, so we're a little in the transition time because we had these three, there's AECOM climate, AECOM weather, DA, and now under everything, there's some emissions, some metadata, something, because people did different things. But we want to make it more homogeneous so that it's on one place. So again, it will be a little painful for the users because they again have to maybe change their path. But hopefully, actually, that will be the last time that we are doing that.
Yeah, hopefully in future it'll all be in one location, that if we need to migrate it again, it'll migrate. So,
but it will make it actually save some disk space too, because then we don't have to all look at different disks.
Okay.
Produce stuff.
And we'll share these slides, I'm sure, afterwards. Yeah. People can have these links to these resources. Yeah. So these were some points that we came up with that we might want to discuss. I'm not sure if anybody has particular burning issues that they would like to discuss right now. We were thinking about talking about necessary developments, any model into comparisons, potentially improving or making sure we have the right OH in the chemistry modeling. If there are any questions about CMIP7, particularly, for example, what Wacom needs to do in regards to CMIP7, and should we support a 2-degree version of the model, considering how expensive it is? And then if there are any questions or discussion points about diagnostics, ADF that we just heard about, or the Melodies Monet, which is a joint project with NOAA that we're collecting pipe and diagnostics as well. So I don't know if we want to discuss any of these or if there's other points. Yeah, Doug.
Just a question about CMIP7. What is the top model going to do? Are they going to do all the runs for CMIP7?
Yeah, so at this point, if we can get the mid-top model tuned, then that's still the plan. The mid-top model may get some upper boundary conditions from Wacom.
But that means you have to run Wacom.
But you can do that from a 2-degree model version.
Okay.
You know, the upper boundary conditions, that's what needs to, maybe that has to move to a Wacom meeting discussion because not everybody is here from the Wacom group right now.
Okay.
But that would be something that needs to be resolved at least sooner than later. What do we need from Wacom? And if the mid-top model provides everything, that means this working group has to do this, the ChemCam working group, probably we will ask help from Sean there too then. So if you need any ADF help, do that earlier than later before he's committed to other things like model runs.
Another question, Doug, for someone like you, not for someone like me who knows nothing about this, but there's been a question of what Wacom itself might want to do for CMIP7. Not as not as input, not runs that would serve only as input, but what would be useful runs for Wacom to contribute, and as not at all an expert in that area. I don't want to make
Well, we haven't seen exactly what CMIP7 is proposing either, so we don't know the scenarios. Of course, we'll probably run the hindcasts and the a forecast, but to run all the SSPs and all that kind of stuff may or may not be in the.
Yeah, and I think the model version will be the question, right? If it will be a 1-degree middle atmosphere version that has different applications for different MIPS, because you also want to do, there's GeoMIP or other things that need maybe a high top model, but then Wacom X may be interested in what Wacom is doing too.
Yeah, so at some point we should have this discussion. I don't know, there was some at one of the co-chair meetings, some preliminary chart of maybe proposed experiments. I assume we can share that with you. I don't know if you've seen this.
No, I haven't.
And I think that was where this discussion came up of, if we were to run all of these, how much it would cost, and really it's not possible. So then we'd have to make some selection of, and what, specifically Wacom would want to do on its own. I think we need some input from community in terms of what would be useful. I'll see if I can find it.
Okay, that'd be great.
I think people are probably hungry, and thanks for sharing that. I hope that was still useful for everybody to see. think we should probably resume the meeting for today unless somebody else has something urgent online or here. I think that's good. It was great to see everybody. Thanks for making it, whoever